session will begin shortly.
So actually, we have something about 153 participants,
Okay.
and all are joining only.
Okay.
That is the reason I just kept some time.
Okay.
And few are watching in YouTube live also, because we can admit a maximum of 100 only here. Others are watching in YouTube live also.
Okay. Okay. Fine, sir. Yeah, fine. Okay, sir. Shall we start now or shall we wait?
Just 1 minute, I will start.
Okay, sir. Fine, fine. No problem.
All are joining actually.
Fine, sir. No problem.
Good afternoon to one and all. Welcome to day 6 session of Organic Semiconductor Innovations, a faculty development initiative sponsored by AICTE Training and Learning Academy and organized by Central University of Tamil Nadu. Today, we have three plenary lectures. The first lecture will be delivered by Mr. Selvakumara S, Product Development Head, Research Supporters India. Before proceeding to today's lecture, I would like to introduce the speaker. Mr. Selvakumara completed his engineering in electronics and communication and started his career in 1999 at Acutrol System Private Limited. After that, he worked in various reputed companies such as Advanced Tech India, Micro Devices Metrom Limited, Advances International, Amitech India, and Biologic India. After 20 years of experience, he started his own industry, Research Supporters India, providing comprehensive solutions for energy research applications, and he is currently the head of product development. In addition to this, he obtained a certificate in electrochemical impedance spectroscopy from University of Bath, UK in 2013. A warm welcome to you, sir.
Thanks a lot. Thanks for the nice introduction. Let us now move into our presentation. Today, actually, we will be covering the topic like hydrogen generation and utilization. Let me share my screen with you. Is it visible?
It's coming, sir. Uploading. Yeah, it's visible.
Fine. Yeah. So we wish to throw some light on the very hot topic in India now. Like this is hydrogen energy, hydrogen generation and utilization. We just named it as generation and utilization. So far, what we have seen, like in past 20 years period, like we must have seen many fuel cell application topics. Many during the many lectures or seminars or conference congress, they used to discuss more on that fuel cell, how to utilize the fuel cell, and then where we can use the fuel cell, All those things are being discussed. But past 5 years, like in India, like you must have like heard about like the hydrogen generation, how to generate the hydrogen, because that utilization fuel cell comes into picture where how we can utilize the hydrogen. But whereas this like hydrogen generation part, so here we have to generate the hydrogen to utilize to utilize in fuel cell or any other applications. Past 5 years actually it is picking up a lot, and then there are a lot of research activities are going on. Not only research activities, so many commercial activities also, like how to generate the hydrogen, the generating hydrogen part commercially viable, and then it is already started in India itself. So we will see one by one in our next slides. So I have like already I got introduction about my company, and then about my profile. So let us move into this next slide. So why this hydrogen, like the topic hydrogen comes into like it is regarded as one of the hot topic in India now. If you see the energy sector, like it is hydrogen energy is one of the most hot topic. Like the past 20 years, many people like so many research taking place in lithium energy, lithium ion batteries, sodium ion batteries, aluminum air batteries, various metal air batteries, various topics have been covered in last 20-25 years. And then fuel cell also, of course, it got some prominence in past 20-25 years. But now recent past like 4-5 years, like there are a lot of interest shown by many private companies, even the government, getting into this hydrogen energy part. Why? The reason is National Hydrogen Mission. Actually, there was this National Hydrogen Mission was launched by the government of India during 2021 to make India a global hub for green hydrogen production. Because whereas India has got more better chances than any other country for green hydrogen production. So this commitment for government of India is to generate 500 gigawatt of renewable energy capacity by 2030. Mainly this is from the hydrogen production. And then so in order to achieve these things, actually government have made a roadmap, and then there is some PPP, like private public partnership, and then private government partnership, government backed incentives to scale up hydrogen production and adoption. So these are all things happening in last 4 years time. So that's the reason actually that is become like more hot topic. The hydrogen energy is more hot topic in India. Like now it is like we can say like it is now overtaking the other technologies like lithium ion battery research, sodium ion battery research, where other battery storage research. Like that was regarded as one of the most highly interesting topic for all the researchers. Now the people are getting more attracted towards this hydrogen energy because of mainly this reason. Like the government is paying more interest on this hydrogen energy. Because why the government is paying more interesting, like paying more actively working on this. Like if you see this there are two pictures. One is that right side is that our central minister Nitin Gadkari is introducing like the first green hydrogen based advanced fuel cell EV Toyota Mirai. Like maybe a year back this function took place. And then left side, if you see this green hydrogen mission, whatever we have seen, with respect to that, there was some conference also like took place in Delhi, and then our team fortunately got opportunity to attend this, and then we got some good information like why the government is paying more attention on this hydrogen production. Because the green hydrogen production, when it is being made, like actually it is not only going to be used only for the automobile in fuel cells or a fuel cell car. It is going to be utilized in a broader like spectrum. Like they are planning to export green hydrogen. They wanted to use green hydrogen for various other purpose also. So that all those topics were covered in this international conference on green hydrogen, took place in Delhi during September. So we will try to explain you one by one now. If you look at the left side slide, that the potential locations identified by the government of India for green hydrogen capacity installation, like mainly the government is setting up hydrogen valleys across India, especially on the coastal side. So they are operating in Gujarat, Maharashtra, and then they are planning to set up something in Kochi and then Visakhapatnam. So where various places they are setting up the hydrogen valley, and then many research is going to take place in this green hydrogen applications. What they do in this hydrogen valley, that the question is they pay more attention on hydrogen, green hydrogen production research, and then the green hydrogen production, and then the export of green hydrogen production from that respective region, especially from this port regions like Gujarat, Maharashtra, Kerala, Andhra Pradesh. They have more, and then even Odisha also, they are identified as more prominent place for exporting the green hydrogen to other countries. So if you look at this is the roadmap for India, the government has given some roadmap for them how to produce the green hydrogen. May try to focus try to focus on this research area, because it is going to play a major role in Indian economy, and then it is going to play a major role in Indian green hydrogen export. So the reason why we are covering is why hydrogen research is more important. That's what actually we wanted to give in a glimpse of the reason why we need to pay more attention on green hydrogen research before getting more into the technical part of green hydrogen production and fuel cell. Now, as we discussed earlier, the government is paying more attention on green hydrogen production, and then what they are going to do while they are exporting, who will be the buyer, why they should buy, why should we import, why should we export the green hydrogen? The main reason is now there is a concept of green steel, green fertilizer. Such a green product, the green product means that green products such as green steel and green fertilizers refers to industrial goods produced using low carbon or carbon neutral process. For example, in steel industries, what we have seen is there are a lot of melting process, various process high temperature, where the requirement of high temperature is very much important, and then they are using maybe natural gas or electricity derived from the thermal power sources. So they are not green in nature, so that they are being used. But since they wanted to reduce, they wanted to cut this usage of carbon emission methods, so they wanted to utilize this hydrogen as an alternative for this. So for that they need hydrogen, and then the hydrogen should be derived from the green renewable sources, that is called green hydrogen. So the export of green hydrogen is more important, because all the government, the whole world is paying more attention on using the hydrogen as fuel in place of other fossil fuels, hydrocarbon based fuels. So that's how this green concept is evolving. All the European countries, they will be forced to buy green hydrogen. They will be forced to use green hydrogen for their metal production or fertilizer or many other industries also. They will be forced to use green hydrogen. So then the India will have the upper hand when they have the technology for the green hydrogen is being developed in India. So that is going to be exported. So that is the main reason actually government is paying more attention, and then so it is an opportunity for all the researchers in India, they can make use of it. So mainly this this process leverage the renewable energy sources and the innovative technologies, particularly green hydrogen, to minimize the greenhouse gases emission. So this is the main motto, and then Mainly the European countries are like paying more attention on this. So there is a great amount of opportunity for India to export green hydrogen in near future. Already there are many different companies, private companies like L&T, Sterling Power, Reliance, Adani, many other like even HPCL, IOCL, they are all paying more at very much focused on this research, and then they are all setting up their own R&D lab and then production labs for green hydrogen export. The reason is actually we are already involved in supplying many instrumentation and software and then production technologies to these companies. So what is green steel? Already as we discussed, like what is green steel means like the steel produced with minimal or zero carbon emissions, primarily using green hydrogen instead of traditional carbon intensive methods like coal-based blast furnaces. Blast furnaces, they used coal-based fuel or sometimes natural gas or sometimes that electricity derived from the thermal power plants. So they wanted to cut down the use of such a power from the to avoid the green emission. So green fertilizer also almost the same like green steel, manufactured using green hydrogen and renewable energy sources. Similarly, the green cement, green chemicals, there are many many applications are evolving. So there is a lot of opportunity available for green hydrogen utilization. So the India is paying more attention on this, and then we have a lot of opportunities being created for hydrogen production research. If you see, this one is from the directly from the website of, like I just copied from the website of Tata Steel. Tata Steel is already like started working on it, and then we also, our company had a visitor from Tata Steel for hydrogen production some discussion. So like this, similarly we had a visitor from fertilizer company also, Nagarjuna fertilizer company also. So it seems like commercially the people are like in India also, they started paying more attention on using this the green hydrogen, how to make use of this green hydrogen for their applications. So to use green hydrogen, we need to make the green hydrogen. So how to make the green hydrogen is another topic that we will cover little later. And then so far what we have seen is like that the green the hydrogen can be used for that green steel, green chemical, green fertilizer, green cement. There are many topics we have covered where the hydrogen can be used as a fuel in place of other fossil fuels or hydrocarbon based or coal based fuels. But whereas there is another interesting application is being evolving, how this is very important, like why we need to pay more attention on hydrogen production research is essential along with the fuel cell research, because so far hydrogen research in India actually more for a fuel cell application, how to use the fuel cell when by using hydrogen as a fuel. So the fuel cell topic was more attractive topic in India, as people wanted to utilize hydrogen as a fuel in fuel cells. But more importantly, the application of fuel cell in real time, it is still has a lot of bottlenecks, and then it is expensive, and then in India it may take maybe another couple of decades to use fuel cell as a power generator, because it is so expensive and then not user friendly also as of now. So we need the utilization of hydrogen, like the fuel cell usage of fuel cell takes little bit more longer period. But before that, there are many applications like
Sir, it is muted.
sorry sir, anything like
No, it's a mistake. Okay, we muted it.
Okay, sir.
Okay,
Right.
sir.
Shall I go ahead? Okay.
Yeah.
Yes, sir. Yeah. So that's what actually the so far what we have seen, like in India, many research research activities are taking place for fuel cell, like how to use a hydrogen as a fuel. But now this hydrogen production research is we can say it is overtaking the fuel cell research, because in past 5 years we have been in this field for past 25 years, from maybe right from 2000 to 2018-19, fuel cell research exists. Like mainly the people were more working on this fuel cell research, how to use hydrogen as a fuel in fuel cell. But since 2019 it started picking up, and then now we are seeing like this electrolyzer application is like more a hot topic, how to produce the hydrogen, using using where we can call it as a method where we can call that hydrogen as a green hydrogen. So the hydrogen production is now that research is overtaking the fuel cell research. So that's the reason actually we need to do more essentially. It is more essential to study about the fuel cell along with the hydrogen production, how we can do it. Because now so far what we have seen is like a green steel, green fertilizer. There are all some applications. And then predominantly what we have seen is the fuel cell can be used in the automobile applications. We have already seen fuel cell cars, even fuel cell trains, fuel cell buses. Fuel cell buses are available in, like it is running in Delhi, with developed by IOCL. Fuel cell car, fuel cell car is being used by our honorable central minister. And then commercially it is available in Europe countries, many of the Europe countries. And then one of the Europe countries already running a fuel cell train in France, if I'm right, France, between the France and Germany. So there are many applications for the fuel cell, using hydrogen as a fuel for fuel cell. Without any combustion, that hydrogen is converted into electricity. But there is another important major application evolving is hydrogen engines, like how to use hydrogen as a fuel in IC engines, like internal combustion engines. So far uh, conventional engines what we are using is like the gasoline engines, like petrol engines, where that combustion take place and then the engine operates. In the similar fashion, they wanted to substitute hydrogen as a fuel in place of gasoline, or in hybrid method. There are actually currently that hybrid methods are in use, but soon this pure hydrogen fuel operation also might come into picture, like soon. So what is a hydrogen IC engine? So hydrogen internal combustion IC engine are gaining traction as an attractive pathway for decarbonization of the mobility sector and achieve carbon neutrality. Because when we burn this diesel or petrol, that is actually we know this carbon monoxide and then many other like greenhouse gases, it's not good for our environment. So this hydrogen internal combustion engines are really good, and then comparatively they are very less uh, greenhouse gases production using when you use hydrogen as a fuel. So this is the main benefit of hydrogen IC engine, is that it can utilize and then the main thing is actually it will utilize the common parts. Like already we have the know-how of the IC engine. So the same way we can use the hydrogen fuel in the normal IC engine itself. So there is no complications, and then easily they can they are like planning to in the existing engine also we can use this hydrogen. That's what actually the research is going on. We had an opportunity to discuss with Ashok Leyland people. Actually, we are located in Hosur, just next to Ashok Leyland. So they are also very much confident. Like in next 3 years, this will we can see this hydrogen automobiles in automobile sector in next 3 years. There are real chances, because currently that the hydrogen storage is the main bottleneck. So that they are like the high pressure storage is the main bottleneck. So that they are like working on how to get rid of it. Once that is done, then there is a real possibility to see this high IC engines in India itself. Currently, it is available in abroad, like on research grade vehicles are being utilized. But in India, it may take some time, but it is not too far. Like soon, we will be able to see this IC engine using the hydrogen fuel in Indian roads. The next slide shows the reality, like how that. And Ashok Leyland person said, like soon it is going to come in next 2-3 years. This is this news I have seen in the newspaper on December 11th, just 3 days back. Bairava, India's hydrogen IC engine test bed facility goes on stream. So they have set up this new facility in Pune for testing the IC engine using the hydrogen fuel. So this is very interesting thing, interesting topic. So far, what we have seen, this high diesel, petrol, this gasoline, like hydrocarbon-based fuels, maybe like may see this hydrogen fuel as an alternate. So soon we'll be able to see. That's what actually the news gives the informations. When you are connecting the dots, actually the reality is not too far. So we'll be able to see this IC engine application also for using the hydrogen fuel. So that's how like this hydrogen fuel gaining the very high importance. Like if you see like this picture, like this shows like good like already hydrogen engines, commercial engines already they have introduced. And then if you see this picture, like this is available in the YouTube also, the nice video. This Yamaha introduced a IC engine, like IC engine using the hydrogen fuel. So this what you see is this hydrogen tanks. Now this Cat 3. So the Cat 3 tanks actually being used for storage. Cat 4, like Type 4 tanks are being used as per the international norms. So in India, actually there are some regulations. Actually, some certifications are being like pending. So once that is cleared, and then once this high pressure usage of this high pressure Type 4 cylinders in normal automobiles, then we have a possibility to see the IC engine on the roads. So already these commercial products are already made, already being sold for some application, in few applications. So the hydrogen fuel usage of hydrogen fuel applications are not limited only to the fuel cell. Actually, it has got many other applications. Like fuel cell is one of the applications where we can separate, like where we can convert the hydrogen into electricity. But whereas it can be used in IC engines, it can be used in steel industries, cement industries, fertilizer industries, many other industries. So that is playing like a major role, this hydrogen production. So what we have seen in our in ground reality, we have seen like past 4-5 years, this hydrogen production research is overtaking the fuel cell research. So like maybe it may not be a bad idea for paying more attention and then throwing some light on hydrogen research if someone wants to like start the hydrogen production research. So we have seen why we need to pay more attention on this hydrogen production research. So now let us move into more technical part, like how we can generate the hydrogen, what are the different methods, and then what are the components required, what are the components of that instrumentation, how it can be tested. So all those things we will see in the next slides. So as we have seen, the hydrogen, a key component of most of the renewable energy sources, as we know all these things. So now this hydrogen can be produced mainly, like I just there are many different methods are available, but I just since I have only limited space, so I have mainly just categorized here like biomass, fermentation, already this methane like type. hydrogen production is can be made. And then the photoelectrolysis is another method. And then these two methods are like, we can say, like more on R&D side, or not for the like high amount of production. These two methods are like not good for like a very not very much popular, and are not like suitable for this high amount of like a very high hydrogen production methods. These two methods are not suitable. But whereas this another method, like the electrolysis method, is the key area where it is being used for like green hydrogen production. So for the electrolysis, we require the electricity. So for during use electrolysis method, we produce the hydrogen. The electricity is being used. If the electricity is being derived from the renewable energy sources, whereas like windmill or hydro or solar, like from these kind of like renewable energy sources, if you get the electricity, and then if you use this electricity for electrolysis method, then it is called green hydrogen. So that's how it works. And then that's what that electrolysis method is the more prominent and then widely used accepted method, and then it is proven method for production of green hydrogen. But whereas these two methods are not so popular, and then not suitable for high amount of like large quantity of hydrogen production, they are not very much suitable. So how the hydrogen is produced and utilized? So we need like because we can produce the hydrogen using the normal power also, like the domestic power where we are having like 230-volt domestic power also, we can convert into DC, we can use it. But they are not called as green hydrogen. The green hydrogen has to come from the solar panel, or from the windmill, or something like that, or from the electrolysis method, or photo electrolysis method. So different method we require to generate the hydrogen. So once the hydrogen is being generated, already we have seen like the applications where we can use. We can use it for mainly we can use it for fuel cell to convert the hydrogen into electricity. Mainly, actually, this fuel cell producing the hydrogen using the electricity, and then converting the hydrogen into electricity using the fuel cell. Here, the application is one is automobile application. Another application is like whereas like the army people, or where the remote area where you can't access easily, that where you do not have like electricity connections. So there they can use, they can produce the hydrogen during the sunlight, using the sunlight during the day, and then they can store it in the cylinders, and then that stored hydrogen can be used as a fuel to generate the electricity whenever they require. This is one of the application, especially not only the in addition to that automobile application, this is one of the very interesting applications. Already Indian Army also using this fuel cell technology in the remote locations in our border, and in a very Kashmir, and then other remote locations. So hydrogen has got many applications, and then fuel cell is one of the main applications. So the produce hydrogen, green hydrogen, as mentioned, that the photolysis process. This is actually not like this more still in like R&D only, not developed as a commercial product. Still, people are doing some research, and then like photolytic process involve the use of light to break the water into hydrogen and oxygen. And then you can divide into two models. One is photobiological water splitting, and then photoelectrochemical water splitting. So the photobiological water splitting involves the use of sunlight and specialized microorganisms such as green algae to split water to produce hydrogen. There's some interesting topic, actually many people are working like but so far, honestly speaking, so far no commercial product available. But you can't ignore it, because actually this also having a very much it's an interesting topic. And then like getting like more attention from the many researchers, like maybe in future, if there is any commercially viable ROI, return of income, is achieved using this method, then we can say. But as of now, there are no commercial products are available. But on R&D scale, many people are doing this research. Photobiological water splitting. Another interesting topic from this photo is like photo electrochemical water splitting. This is more more attractive than the photobiological, because photobiological has it generates very little amount of hydrogen. Then the amount of hydrogen being produced out of that application is also not too much. But whereas this photo electrochemical water splitting, this is more one of the interesting topic. And then maybe I'm not very sure, but I have seen couple of commercial product available in the northern part of Europe countries, like where they are using this photo electrochemical based water splitting setups. This is actually basically working on HCR and OER. We know, like this is HCR and OER. We know, like hydrogen oxygen evolution reaction and hydrogen evolution reaction. This is a very simple half cell method that is being used in this photoelectrochemical water splitting. Photoelectrochemical water splitting uses sunlight and the photoelectrochemical materials to produce hydrogen from the water. This photoelectrochemical panel has got an anode and cathode. The materials are coated on it, on it. Then the light energy is used by the photoelectrochemical material to completely separate water molecules into hydrogen and oxygen. So that's how it works. So whereas you see you will be able to collect the hydrogen from the cathode side, and then the oxygen evolves from the anode side. That's how it works. Currently, this research is focused on discovery of photoelectrochemical materials with the correct energies to split water, while are also stable when it comes to contact with water. Because that of still it is not this concept is proven. This concept is proven. People are using it, and then we will be able to prove the concept. Proof of concept can be given. But when you wanted to introduce as a commercial product, that longevity of the product has to be proven. We need to use it for a year, 2 years, 3 years. It has to stay stable. So that is not yet been proven. This concept is proven, but so the people are paying more attention on how to improve the efficiency, that longevity of the longer period usage of this material, and then the exact energy required to split the panel over the period, when you are putting it into real-time applications. Slowly, the material will go bad. So how to avoid these issues? So they are doing a lot of research on this materials development. So this photo electrochemical water splitting also another interesting topic, but certainly much better attention it has already gathered than the photobiological what already we have seen, photobiological water splitting. But better than this photoelectrochemical water splitting method is much well proven system. Already a lot of research is going on. Hopefully in soon, maybe in another 5 to 10 years time, we should be able to see some commercial product coming out of this research. So these two research are maybe very not very common methods for generating the hydrogen. But research topics, we can consider it as research topics. Someone wants to take up this research on hydrogen, then that's an interesting topic, and then we can't avoid those applications, because they are very important in future also for green hydrogen production. So another important topic, more than 99% electrolysis method being used for hydrogen production. And then in this electrolysis method, what we have seen is Actually, maybe my next slide explains a little bit in detail. What you are seeing is like a PIM, proton exchange membrane based electrolyzer. So the voltage differs based on the technology, because there are different technologies are there. Maybe we will see. Well, if you look at the technologies, there are technologies are available like alkaline based technologies, PEM based technologies, SOEC technologies, AAM technologies, photocatalytic. There are various technologies. So in this, that PEM is PEM, like the similarly like we are using in PEM fuel cell. This is also similar way like proton exchange membrane based electrolyzer. Normally, like we are using the commercially available Nafion membranes for this. So this is the water electrolysis method schematic diagram, where we have anode and cathode, two separate tanks. And then it is being polarized with like a specific voltage, depends on the anode and cathode, between the anode and cathode. And then that's how the water is getting separated. The water is getting separated, and then the hydrogen, we are collecting the hydrogen on the cathode side, oxygen on the anode side. This is a basic simple schematic diagram, and then the simple way like how we can produce the hydrogen using this electrolysis method. And then if you use this electricity comes from the renewable resource, then it is called green hydrogen. Otherwise, it is not green hydrogen. So that's how it works. So in addition, the heat is actually, for example, like here we are applying the DC power to split the water to generate the hydrogen. In addition to this, like in addition to the power, and then the heat is needed for the operation for an electrolysis cell. Normally, maybe 40, 50, 60, depends on the heat, that the voltage varies, and then the efficiency of the electrolysis, efficiency of the hydrogen production also varies, depends on that. So that's how like it works. Like this is one of the basic electrolysis method. All the electrolyzers like AEM method, alkaline method, or PEM, like this one PEM method, all the methods are almost working in the same principle, but they have their different materials are being used, that we will discuss in detail in the coming slides. So mainly, if you see like this solid membranes which are used in the middle. So solid membranes used in the setup typically are electronic insulators and need to be gas tight. Of course, if this we have seen like that half cells we have seen, and then the full cells we have seen, like how the hermetically sealed anode and cathode. So it should be completely isolated. But this membrane, what the specialty of this membrane is, special property of being able to conduct ions via fast diffusion through the solid. So these are all electronically like isolated, it's like insulated, but they conduct ions. So that's how it works. The proton exchange membrane, protons, like they exchange the protons are being exchanged. So that's the reason actually it is called the PEM electrolyzers. Similarly, almost the operation is something like similar like PEM fuel cell. This is one of the commercial electrolyzer picture. So what we have seen is like why hydrogen is required, and then where the hydrogen can be utilized, and then so for that we need a hydrogen. So how do we generate the hydrogen? We can generate the hydrogen using the photo electrochemical, photo biological methods, and then the electrolysis method is more prominent. So using the electrolysis method, this is the commercial electrolyzers are available like this. Some dabbas like boxes are available in commercial market. It is available. So you can if you wanted to generate the hydrogen, you can generate the hydrogen using this kind of commercially available systems also. So this is the basic schematic diagrams of for the hydrogen production unit. So this is this system, this hydrogen generator box is manufactured based on this technology only. So here you have a like electrolyte, maybe distilled water. If suppose if it is PIM method, the electrolyte is different. AEM method, the electrolyte is different. Alkaline method, you need a different electrolyte. So depends on the electrolyte. Actually, it generates the hydrogen. So this is a commercial product. It is available in the market also. So as we discussed, like there are many different types: alkaline-based electrolyzers, PEM-based electrolyzers, SOEC, solid oxide electrolyzers, AEM, anion exchange membrane electrolyzers, photocatalytic electrolyzers. These photocatalytic electrolyzers are not commercially, so far not very popular, not very much proven, and then very rarely available, not commercially viable or commercially available product. This last one, but all these other four technologies are very important technologies, already techniques widely being used, especially this SOEC is very high temperature application, like 700 to 1000 degree. So here the one ceramic material used as a fuel. So this is very different technique. Actually, mainly this oil and gas companies, they are paying more attention on this. Rest other than this SOEC, alkaline, PIM, AEM, these techniques are very like we can say like prominent techniques. They are widely used everywhere. Especially this alkaline method is one of the prominent method for generating the green hydrogen. Mainly many different private companies already they are working on it using the alkaline method. This both alkaline, PIM, and as well as this AEM method, they are working temperature is around 70 to 80 degree. So it is easily doable. And then the main difference between this alkaline, PIM, and the AEM is PIM technology. In PIM technology, if you see, the cost is high. But whereas the alkaline, the cost is low, and then this AEM also low. Mainly because of the PIM technology uses the PIM technology basically using the platinum as a catalyst. Platinum as a catalyst, so it is a little expensive. And then the membrane that the membranes which are used for in PIM applications, they are also very expensive when compared to the alkaline and the AEM. Currently, the proven membrane is the Nafion-based membranes, polymeric membranes. So polymeric membrane also expensive, as well as the platinum catalyst also expensive. So that is the reason actually, but very well proven method, and then it is highly. There are many commercial systems also available for this PIM electrolyzer, but they are expensive in nature. But and then the one more bottleneck is actually we have to use distilled water in this case. In PIM method, we have to use distilled water as a fuel. Like distilled water has to be used for hydrogen separation. So if you have a normal water, that will not work, and then you need to convert into a distilled water where your conductivity should be or in the order of like microsiemens. It should be in microsiemens. Then only it works well. But whereas this alkaline or AEM methods, they use alkaline electrolytes like potassium hydroxide or sodium hydroxide. So many different different concentration they can use. For alkaline, they can use 5 molar potassium hydroxide. For AEM, they can use 1 molar potassium hydroxide. So that's how actually that makes it. And then the catalyst being used as a nickel is being used as a catalyst, and then the membrane also not so expensive when compared to PIM technology. So that's how this alkaline and the AEM technologies are cost lesser when compared to the PIM and the PIM. When compared to the PIM, SO is also little higher, when compared to this alkaline AEM, and then they are very specialized applications only. Not we cannot use it in normal conditions. They require very high temperature, very high operating temperatures. Mainly oil and gas companies are paying more attention on this. So we have seen like different methods. Like we have seen the electrolysis method is the best method for generating the hydrogen. And then out of the electrolyzer methods, actually there are 3-4 methods we have seen. Out of 3-4 methods, alkaline electrolyzer, AEM electrolyzer, PEM electrolyzer, and then SOEC are more important. But SOEC, since it is very high temperature, today we will cover only the alkaline electrolyzer, PEM electrolyzer, and AEM technologies. So whereas we have already discussed like alkaline electrolyzer. So this is one of the picture of the alkaline electrolyzer. This electrolyzer is already installed in many parts of the world as well as in India. In India itself, if I'm right, actually they have at least maybe 10-15 installation, no, not 10-15, even more than that, like NTPs.
The PEM electrolyzers electrolyte will be like a solid polymer membrane that will be having like the distilled water will be split into hydrogen and oxygen. Whereas this SOEC, solid ceramic metal, will be used as an electrolyte. So that's how this electrolyte also varies, depends on the technologies. Then the membrane and separators, what kind of membrane we use. Alkaline, we use non-conductive porous diaphragm. PEM, we use proton exchange membrane. SOEC, we use some ceramic electrolyte, dense ceramic electrolyte. So that's how actually it operates. Like the technology is same, the method is same, the model is same, but depends on the technology, depends on the type we use, we change the materials for this. And then the bipolar plates. Bipolar plates also actually we use different types of bipolar plates, like stainless steel, titanium, or coated metals for corrosion resistance. Hello?
John, please block that some noises coming, John. John, please block that.
Okay. So we have seen this bipolar plates, various types of bipolar plates, various so stainless steel, titanium, or coated material for corrosion resistance we are using. And the current collectors also like
Dr. Kunnar, so can you please block?
Yeah, current collectors we are using the current collectors like various different material, mainly corrosion resistant conductive materials like titanium or graphite used as the current collectors. So there are if you see look at this current collectors or any other material like bipolar plates, still a lot of R&D is going on. People are taking new materials to do some R&D, and then they are making use of some different coating methods to improve the corrosive resistance. So it has got a lot of research scope, not only on the chemistry part and the mechanical stability, corrosion resistive material development. So it has got a lot of scope on the electrolysis part from the R&D perspective. And then the current collector we have seen, the next is GDL. Like the GDL is gas diffusion layer. The gas diffusion layer, of course, we must be knowing it facilitates the transfer of reactants, water or steam, and products like from anode to cathode, cathode to anode, that takes place at the gas diffusion layer. And then the stack, we need to develop a cell, and then the cell will be stacked together for a higher current, higher voltage, and then repeating continuously we connect it in series for making as a complete stack. So that this is more of here a lot of mechanical and mechanical engineering scope, research scope also available in this stack development. And then water supply system. Water supply system, it is how you provide the supply the water. Suppose if you supply the water to your cell continuously, distilled water may not be an issue. But if you are supplying alkaline solutions like 5 molar alkaline solutions, that itself a really challenging task because your materials will go bad and then you have a corrosion. You have a disconnection after maybe the usage of 6 months, your pipe will get damaged. So all those things have to be taken care. So this has got like a lot of very much attractive research area for mechanical engineering, instrumentation people. So there are a lot of research scope available for the water supply system. This is one of the important portion in the electrolyzer. How do we supply the water? And then the power supply. Of course, we need electricity to like split the water. So for that purpose, the DC power supply is required. In normal smaller case, actually we have you can use like normal at lab scale, we can use the programmable power supply. But whereas in industrial grade, like the LNT and all, they are doing maybe around 100 kilowatt, 1 megawatt splitting, water splitting. So for that, they cannot use this normal DC power supply. They have to generate the DC. Usually, like there are a lot of electrical engineers importance comes into picture. How to convert the AC into DC and then regulate it into DC, supplying the DC all the time, like controlled DC application. All those things comes into picture: rectifiers, inverters, power electronics. So there is a scope for a lot of scope for electrical engineering also in this power supply system. Similar way, there is a cooling system because it is generating a lot of heat, and then the heated electrolyte pumped into the cell for reaction. Once the reaction completes and then that comes out, and then we need to take out the heat, and then we need to pump it back. There will be some recirculation process will take place. For that, we require coolant circulation pumps, heat exchangers or radiators. Many different components are required. So here is the scope of a kind of automobile engineer requires or a chemical engineer. All those things like all those engineers will come into picture. Similarly, and then once the hydrogen is generated, and then we need to remove the gas collection and the separation system. As we have seen that electrolysis method, we are pumping the electrolyte and then we are splitting the water into hydrogen and oxygen. Once the hydrogen is generated, and then that hydrogen will carry a lot of moisture and then water droplets also. That has to be removed before using the various gas separators or demisters or various different methods. So this is another another research area where we can pay more attention. And then the control electronics. There's all these things requires control electronics, software, this power electronics. All these things are required. So the electrolyzer is one of the has got various types of components, and then providing the if you see from the material development, electrolyte supply, membrane, bipolar plate development, then mechanical engineering. So various, actually it provides the research opportunities for various engineers, various domains, not only for the chemistry. Actually it has got a lot of domain to work, it expands a lot the research scope of a person, from any domain they can select, even a mechanical engineer, electrical engineer, material developer, chemical engineer. So they all playing important role in electrolyzer development. Still India now only started taking baby steps, and then this is a good opportunity for anybody who are looking to enter in this hydrogen research. This is a good time, and then maybe they can see a good future in electrolyzer research applications. This next another one is we'll get into this fuel cell. Fuel cell, as we know, the fuel cell is is used to convert the hydrogen into electricity. Of course, in the similar electrolyzer, the fuel cell has got various types of fuel cell: PEM fuel cell, SOFC fuel cell, DMFC fuel cell. SOFC means solid oxide fuel cell. PEM means methanol fuel cell. There are various different different methods are available. So more widely accepted and then used method for widely used method. Here, I hope you must have seen these slides already before, like from the previous presentations. So, like when the hydrogen gas is supplied at the anode, and then the electron and proton is being separated. The electron will take this route like via load, and then only the proton via the proton exchange membrane. Only the proton transported to the cathode side. Again, from the cathode side, electron and proton getting connected, and then we get the water as output. And then the electron is bypassed. It is not allowed to travel via this membrane. So the electron is taking other route. This is where actually we are capturing the electron as electricity. So this is a basic funda. Of course, you must be knowing all these things. So this PEM fuel cell uses water-based acidic polymer membrane as its electrolyte with platinum-based electrodes. Similarly, right, electrolyzer also we have seen that PEM electrolyzer uses platinum-based electrodes and then catalyst. Here also this PEM fuel cell also using this platinum-based electrode. So that is the reason this PEM method is a little expensive when compared to any other method. But this is the one prominent and then proven method as far as the fuel cells are concerned. Of course, there are other methods like phosphoric acid fuel cell, DMFC. There are various methods, but this is more proven and then more viable solution in fuel cell technology. Other fuels like alkaline fuel cell, phosphoric acid fuel cell, solid oxide fuel cell. Of course, solid oxide fuel cell is like one important technology we can say that is used mainly. But as we have seen, like that solid oxide fuel cell, we require very high operating temperature, around at least 650 to 850 temperature is required. So that is the reason actually it limits its applications. Only very few areas it is being used. Other technologies are like not very popular, like not commercially viable technology. They've tried to use, but they were not so popular as like PEM technology. So that's the reason mainly people are using this PEM technology. And then if you look at this applications of fuel cells, like they are used for portable applications, they are used for stationary applications, and then they are used for like transport application, automobile applications. So there are various different applications. The portable applications are like it can be used in remote areas as like a UPS or like as I mentioned, like in army, Indian army also is using many countries. They are using this fuel cell to power the remote areas, like remote locations where they cannot provide the direct power using the cables. So this is more easiest way to generate the power. So when you wanted to use this portable one like PEM fuel cell, DMFC, direct methanol fuel cell, SOFC, they are really good. And then when you wanted to use the stationary, like stationaries, of course, you wanted to power a room, building, or something like that, where you need power in terms of kilowatts to megawatts. Then also actually, of course, PEM technology is more prominent one. In addition to that, alkaline fuel cells, molten carbon fuel cells, phosphoric acid fuel cell also will come into picture, but they are not very commonly used like PEM. PEM is more prominent. More than 90% people are using PEM only. And then the transportation. For transportation application, no other technologies will come into picture. Only PEM. And then DMFC, of course, that DMFC is like a hybrid kind of PEM, like along with the PEM that uses, which uses that methanol as fuel. that has got its own limitation, but the PIM is the more prominent one. Already currently the trains, buses, all transportations that are being using fuel cell, they are using this PIM technology only. So PIM is more prominent and then more proven technology. So currently we can see in future, like maybe this PIM fuel cell will come into picture for automobile application. But sooner, like already we have seen this PIM, IC engine, hydrogen IC engine also like on the cards. Maybe we don't know like what will happen in future, but still this fuel cell is currently very promising technology in future, because there is no combustion, and then this output is only the water, so absolutely zero emission. So the fuel cell holds a very prominent place in this, or especially for automobile applications when compared to IC engine. And then if you look at the technology, like how do you rate this fuel cell technology application? What are its strength, weakness, opportunities, and strength, threat? So suppose if you look at the strength of this fuel cell, PEM fuel cell is the fuel cell converts the hydrogen directly into electricity produced at site. So easily, it is very easy. Like just name it. Like you just supply the hydrogen, automatically you will get the electricity. Very very simple. No burning, nothing is required. Just it is simple as like you just supply the gas, take the electricity outlet, and then inexhaustible source. So inexhaustible source. So it's not like a fossil fuel or like a depleting resource. It is always available in abundant. Like we have water, so it can be easily made, and then it can be recycled also. And then sustainable development strength and diversity in resources hardening. So they are all the great strength of these fuel cells. And then what is the weakness? If you look at that, what is the weakness? Unavailability of an efficient hydrogen infrastructure. Like because, for example, like storage of hydrogen is too dangerous, and then it is not widely available. And then there are so many government policies are pending, especially in India. It is not accepted policies are still available for using hydrogen, type 4 hydrogen tanks in many applications. So that's what actually here storage of hydrogen is little high cost, whereas in this hydrogen technology, storage of hydrogen is more tedious process and then cumbersome process. So that's the really we can say currently that's a weakness for this technology, why it is not so popular. Otherwise it would have become very popular by this time. Storage is one of the great bottleneck. And then if you see the opportunities, of course, it has got a development potential, improve the energy security because it is not depleting. And then carbon emission is nothing. A new and then having more it's more futuristic. And then over the period when the hydrocarbon fuel is become expensive, then this become more it will become cheaper when compared to that in the during the course of operation. Maybe after 20 years, 30 years, this may play a major role when compared to the fossil fuels. Threat, negative influence, actually mainly why it is not, why already it is available but still it is not so popular among the public is like many people like feel like that hydrogen, how to use the hydrogen, and then the lack of awareness, and then the safety issues. People are like even many people asked our when we go for installation also, they are like very much afraid of using that hydrogen cylinders. Of course, it has got like its own like limitation, means safety concerns are there. But if it is used in all the norms are followed promptly, then there is no issue. So that negative influence has to be removed. It's good, like our central minister himself is using that Toyota car. That's an added advantage. Like that will improve the confidence among the normal public will get more confidence on using the hydrogen vehicles on other applications also. If you see like that fuel cell vehicles are already in place, so many fuel cell vehicles are already introduced, not only on concept wise, but in Europe already commercially it is being used, it is available. And then this is on a hydrogen, like a hydrogen train. This is already running train between built by Alstom. It is if I'm right, it is running between the France and Germany. I'm not sure, but it is already operational. And then if you see like there are some other fuel cell for domestic applications, what you see is like this Toshiba. What you see is like of course this is very old product. Now this product is obsolete. Nobody is buying. But this product was introduced during 2003 or 4, if I'm right, because I got this picture. I have been using this picture since long time. 2004, I got this picture. This is a DMFC application. DMFC DMFC fuel cell, where when you have the methanol inlet, and then automatically that methanol will be converted into electricity. Then this is a iPod, I think, kind of like media player. So you can use this methanol liquid as a like electrolyte to generate the electricity. So like this, what you see here is like this is a electricity generator. Your inlet will like a hydrogen when it goes inside the machine like a fuel cell, and then you will get the power out like 230 volt like a generator. Now this petrol generator will be similarly hydrogen as a fuel, and then if you see a generator, hand carry generator are already used in many applications, especially the remote applications where the where they do not have access for the normal electricity. Wired power connections are not available. They are there. They are using it. So the applications of the fuel cell are not limited. Actually, they have a lot of many applications, not only automobile. And then the fuel cell will be used in the many domestic applications, stationary applications, portable applications. There a variety of applications are available. If you look at, there is a comparison I have seen, like an interesting comparison between the hydrogen fuel cell and then lithium-ion battery. Why it is not so popular, and then how it is going to become in future. People will pay more attention on this hydrogen fuel vehicle, because currently this lithium-ion batteries are like called green cars. Like they don't generate any. There is no combustion. There is no emission. So they are really environmentally good. But whereas this hydrogen are not popular because mainly because that car price, because this car prices are like from the US website I have taken. So approximate cost of the hydrogen fuel cell vehicle is $60,000. Whereas in India, I think it is around 60 or 70 lakhs, more than that. Whereas this electrical vehicle cost 1/3 of the hydrogen vehicle cost. And then the running distance, of course, running distance also almost the same. In electrical vehicle, the disadvantage is that charging, like times, we know that. But whereas hydrogen fuel cell, it is maybe 2 or 3 minutes, like a gasoline, how we fill the petrol. Similarly, we can fill the hydrogen. So this is the one greater advantage, like a time. There is no time lap, like in electrical vehicle, we need a lot of time. But whereas hydrogen vehicle, absolutely there is no time loss. But whereas the initial cost, that is now the hydrogen vehicle is costing at least 2 to 3 times costlier than the electrical vehicle. But during the due course of over the period, maybe after 10 years or 15 years, if you look at the cost of the batteries might go up, because the lithium is like a depleting resource, and then we are depending on other countries, and then only limited amount of material is available. So over the period, the cost of the electrical vehicle, when it goes up, then the hydrogen fuel cell vehicle will come down. And then when the mass production begins for this hydrogen fuel cell vehicles, then again that will give some formidable advantage for the reduction of the fuel cell vehicle cost. So over the period we can expect this hydrogen fuel cell vehicle also will compete with the electric vehicle maybe in 5 to 10 years period. Not in India, but at least in other countries, US or European countries. And then as already we have seen, like the electrolyzer has got a lot of research scope for various domains like electrical, mechanical, instrumentation, chemical. Similarly, that fuel cell also, it has got a lot of various instrumentation involved in it, like humidity coolant, like the electronics, power supply, like for electrical, hydrogen recirculation for the chemical, all these engineers, and then for control for instrumentation. So it has got a lot of other scope for various research domains. So confidently people can take this as their they can get into this field. So because this now only this field is getting more popular, so they might get like a good opportunity in future. So to test this fuel cells or electrolyzers, we need some test stations. Of course, this is one of our company products. Like we are making this station already. We supplied to Adani, Shell, IITs, many IITs, ONGCs, HPCL, there are various places for testing their hydrogen research components, all these things. So already I think we are running out of time. So let me go through this. Okay. Yeah, we have reached the end of this presentation. So I'm on time. Let us make it more. I thought of giving at least 10-15 minutes for a more interactive session, but already we are late. I would be happy to answer if you have any questions regarding this applications like electrolyzer, hydrogen generation, and hydrogen applications. So I will be happy to answer. Suppose if you have any questions, please try to post it. Yes, sir. Yeah, please go ahead.
Sir, good presentation, sir. About the storage of hydrogen? So
the storage of hydrogen is currently, as I mentioned, there are normal cylinders. What we have seen, these normal cylinders, like oxygen cylinders, hydrogen cylinders. What we are seeing in this commercial market currently available, metal cylinders. They are not used. They cannot be used for the high pressure application. They can be used for only up to maximum up to 16 bar or lesser pressure. But when you wanted to use it for automobile application and all, you need minimum 32 bar, 64 bar, and then it goes up to 320 bar. For a real automobile application and all, they go up to 160 to 320 bar 320 bar pressure. For that, these cylinders are be used. They use type 3 and type 4, especially for automobile application. They use type 4 cylinders. The material they are using FRP, fiber reinforced materials, plastics, not metals. They cannot use it. The type 4 cylinders are FRP and then some different special materials. So only that kind of material can be used for making the cylinders. Those cylinders will withstand very high pressure, right from 64, 160 bar. 160 bar also that can withstand. So we need that kind of cylinders to store the hydrogen. And then to store the hydrogen, we need some special compressors also to transfer the production point to storage point. We need some compression, compressors. So that's how it can be stored, sir. So that's actually again another big topic, like a huge research area where actually now we are lagging. Once we get a clear picture on this storage, then only in usage stage.
Yeah, okay, sir. Thank you, sir. Sir, can you explain the mechanism of photobiological water splitting? You mentioned about the photochemical water splitting only. For biological method, how it's hydrogen gas is generated?
Maybe I'll share you some research papers, because actually we are not currently working on that technology, because this is just they are using some algae, like biological algae, to split the water. Maybe I'll share you more research papers on this. I have, but we are not doing it in our lab.
Thank you so much, sir. Yes. Thank you so much.
Sir, good afternoon, sir.
Yeah, good afternoon. Yes, thank you.
Yes, sir, it's a very eye-opening presentation for the academic people with the industrial background you gave. Very nice. Okay, sir. Sir, my question is, in PEM fuel cells and PEM hydrogen electrolyzer, you are using platinum as electrode. Okay, sir. That's why the cost is very high, and also the application is very limited. So instead of platinum, is it any possibility we can use iron, nitrogen, carbon composite?
Sir, actually, what you said is you rightly asked the question. Actually, that is the main important research going around the globe. Like many people are working, but so far no great achievement using other materials. Even they tried molybdenum and then various different methods also. But so far, the like material output what we require. But other materials so far people are trying. Actually, what you said is iron based composites they have used, but the output is very much less, like maybe 1/10 of platinum. So that is actually that is not viable for them, like because this platinum based method gives 1.023 volt, like basic voltage. So they need at least minimum that voltage to carry out the to move to the next stage. So far there are no alternatives, like viable alternatives found. But iron-based or molybdenum or various other material research works are going on, but not commercially available, sir, so far.
Thank you, sir.
Yeah.
And one more small doubt, sir. Actually, I did a PhD in organic chemistry. Okay. So my topic of the research is amine boranes. And that amine boranes I used for organic reactions, sir. Later I come to know amine boranes are the source of hydrogens. So I know the method of producing amine borane. I can produce different type of amine borane, sir. So is it possible I can collaborate with your industry so that amine borane can be used as an electrolyzer for the future research?
Maybe we can try, sir, no problem. Actually, we are working on an electrolyzer project with many industries and many education institution, R&D institution with the SICRI, IIT Madras. For give idea, suppose if you have to provide a shape, like how to convert that idea into a product. So that's what we are doing. We are already collaborating with many institutions. For we are the technical partners for many DST projects also. Please, you can maybe you can send an email to us, sir. Like maybe you can contact us through the organizing committee. So we'll there are possibilities, sir. Please.
Thank you, sir. Very kind of you, sir. Thank you.
Okay, sir. Shall we wind up? It's already late. I think you will be like getting late for the next presentation.
I hope that there are no more questions. I would like to thank the speaker, Mr. Selvakumara S, Product Development Head, Research Supporter India, for his wonderful and informative talk. We are very grateful to have you here, sir. The next session will be handled
Okay, thank you.
by Dr. R. Bairava Ganesh, Head Process Engineer.
Yeah, thank you. I'm stop presenting.
Head. Thank you. The next session will be handled by Bairava Ganesh, Head Process Engineering, Tata Power Solar Limited, Tirunelveli. Dr. R. Bairava Ganesh as a researcher in Kyushu University, Japan, Japanese government. In 2009, he joined Mosfet Photovoltaic Limited, Greater Noida, as a R&D manager. After that, he worked as an assistant Astra Deemed University, Tanjavur, As a Deputy General Manager for ATAL Solar PV Limited, Ahmedabad, and as a Principal Project Officer at AMOLED Research, Department of Electrical Engineering, process, Tata Power Solar Cell Limited, Tirunelveli. We are happy to have you here, sir. Now, over to you.
Bairava sir.
Sir, you please join.
Hello. Hello.
Sir, you can join now.
Okay.
You can present your slide. Go to the slideshow.
Is it visible? Hello.
Visible.
So, thanks for Professor Nagarajan and Professor Seduraman for this opportunity to interact with the team. Of organic chemist and other scientists to present a few work. Of course, this is not my current work, which I carried out in IIT Madras. Okay, this year. Okay, so the topic of my presentation is AMOLED based displays and overview. Okay, just for the people who are new to the organic electronics, AMOLED meant active matrix organic light emitting diodes. So which are the basic building blocks of displays used in mobile, TV, and other gadgets. Okay, so I'm just going to present an overview, starting with introduction and covering all this the entire technology era of AMOLED based device. Yes, am I audible?
Sir, you are audible, sir. Can you please move to this full screen?
Okay.
Go to the slideshow.
It's showing full screen to me. Is it full screen now?
No. You can better you can close it and you can select the entire screen.
Okay.
Share the entire screen.
Okay. Just a minute. How about now?
It's fine, sir, now.
Okay.
Yeah, please. Okay,
Yeah.
go ahead.
Thank you. Yeah. Okay. To begin with, I just like to acknowledge the funding agencies for their really generous funding. Actually, it was about a tune of more than 50 crores. MAITI, our principal funding agency, followed by DRDO and Tata and Sons. And of course, the location of the center is ARC, AMOLED Research Center in Department of Electrical Engineering in IIT Madras. Of course, along with again, kind of like a funding agency called Grandwood Technologies from United States of America. So these are the major funding partners of this project. Okay. This slide shows my outline of the talk. I just begin with the introduction. Of course, it's not a scientific introduction up to provide awareness towards organic LED based devices. So I will just show you kind of like a branding or marketing of ALOD devices. Nothing more scientific, but just to understand the current market flavor. Then move to the organic. I'm going to emphasize you the usage of organic LEDs, or inorganic and organic. Moving to this is basically covering the physics of organic LEDs, and then the selection of organic materials and devices, and we'll show you some slides on the manufacturing process. And finally, I will just show you the challenges and opportunities which are available in this field. And let me conclude with the take-home message of the entire presentation. So roughly it will take like I will split into 40-20. So 40 minutes I will try to cover this, and maybe 20 minutes we can address some of the questions. The slide, which of course this is mainly on the background and motivation. If you see the top side, so I have shown you the survey which are taken from the OLED market and outlook, which is from the display supply chain group. So you can see the market is increasing and very bullish. So every time you can see this is crossing more than 50 to 60 billion US dollars. And of course, this is a collection of different products starting from notebook, PC, smartwatch, TVs, and again AR, VR applications, tail lamps used in automobile, so on and so forth. And of course, you can see from a small form factor, starting from your watch dial, and of course, ultra large televisions, all the places where you are using the organic light stream. You can see in a mobile phone introduced by Samsung, which is Galaxy S, came with a 4-inch display of again Super AMOLED display in 2010. If I'm not wrong, I'm not a big fan of Samsung. We are at Samsung S23 Ultra or Flip. So Samsung, it came from Galaxy S to different models. And now we are at Galaxy 23, right? So all these Samsung screens basically came with a OLED screen with very super accuracy and high resolution. So this is just to understand the importance of this. I'm just going to maybe, if anybody in the line can answer this. This is just a questionnaire to understand. So when you are planning to buy a smartphone, what things should you consider before buying that? So people will say many. Any answers? Okay.
Battery capacity and memory storage.
Okay. Okay. Yeah. So the question is that why did you choose your current phone? What is the reason? Okay. Some places they say that. What are the spec do you consider? Like mention like screen size, RAM. So if you ask the present college students, they will say selfie camera, right? So the question, have you ever bought a smartphone display? Application like TFT, AMOLED. So these are all like basic, which is revolving around buying a smartphone. Okay. So objective of my presentation is to introduce the fascinating field of organic electronics, because we are very much familiar with inorganic electronics, semiconductors, silicon, germanium, indium phosphide, gallium arsenide, gallium nitride. So we are going to see maybe another 10-20 minutes of basics of the organic electronics, followed by organic devices and how it is fabricated and how it is working. And just to see some of the future scope and challenges. So these are the points I'm going to cover, and this is the objective of the presentation. As I mentioned, these are all some basic mobile phones. Of course, this is the era of AMOLED display where you are seeing all, even from sub 10K phones up to even 1 lakh and above, all the phones are coming with, invariably they are coming with AMOLED displays of different size. You can fold, you can flip, and you can see of different form factors. If you see the history, actually, first OLED product was manufactured by a Pioneer. Of course, Pioneer is a company who are doing automobile audio systems. Then again followed by 30-inch AMOLED display by Sony. And again, same Sony introduced the first commercial OLED TV. Then now you see TV. Again, if you see the high definition TV, suppose somebody who are very much interested in this kind of product, you can see the commercial given by the LG, where you can roll this display inward as well as outwards. And sometimes you can use as a plain screen. Okay, without, when the TV is off, you can roll and keep it somewhere. So this is one of the latest addition from the LG. Apart from that, again, OLEDs are used not in the macro displays, also in micro displays. Okay, so see the three applications which I have listed here. So one is actually for the AR and VR application. Is again this AR used in industries for a kind of like a very meticulous jobs like kind of like a material analysis, kind of weldings and other places where you can use the AR consoles, and of course used in micro displays for snipers, and again smart soldiers program, and again you can use it as a head-on display in PlayStations for getting a real feeling of your the gaming environment. This slide is especially for night owls who are using your mobile battery to the maximum to the drain. So LG came up with a revolving technology called low blue light emitting screens, which means we know that this blue light is coming from your displays are harmful to your eyes. If you are seeing this light for a long time, you may get eye irritation. So LG came up with the brilliant, actually a eye safe, which means of course certified by TUV. So these kind of mobile screens will emit very low blue light, okay, compared to the other mobiles, so that you can use your mobile phone even at night before you go to bed. I don't know how much it is good for a kind of like a healthy life, but of course this is again one of the gimmicks given by the LG. What are the other possible technologies given by OLED? If you see, this is one of the technology. With the previous slide, we have seen the ultraviolet, and here it is near IR emitters. Okay, basically like near IR light based applications. You see, this is one of the pulse oximetry. Okay, so where you have a near IR emitter, and which will emit wavelength close to that, and it's used as a kind of like a oximeter, pulse oximeter, okay, which will give you the pulses. Okay, this is a flexible pulse oximeter to a value of $20, nothing else. Okay, and this is one more application for the hair growth, accelerated hair growth. This is actually iGrew. This is a commercial product in US where people want to increase their hair growth. So you can put this helmet maybe when you are at rest, and maybe like emitting on your head, which will increase your hair growth. Another one is mainly for the cosmetics. So this is again near IR based application, which will increase your skin color. So these are all well proven and commercial applications based on OLED technologies. Let's quickly see the fundamental involved in the organic light emitting diodes. So the basic phenomenon involved in the organic light emitting diodes is electroluminescence. Okay, so here I have given a small sketch of organic light emitting diode structure. So you can see there is a HTL transfer hole transport layer and ETL transfer electron transport layer. So these are all organic semiconductors, so they have a delocalized, okay, the bands we call HOMO and LUMO, okay, and this is similar to your conduction band, valency band in case of inorganic electronics. So when I apply a bias, basically a voltage here, so it will generate electron and holes either in the respective terminals. So the electron and hole should pass through the HTL and ETL and come and meet at the emissive layer, and they recombine at the emissive layer, and the recombination energy layer, and that actually you will form a particle exciton. Why it is called exciton? Because this particle is a result of excitation, electron hole pair excitation. So this exciton will go from the your ground level to the upper level and again relax back to the ground state and will emit radiatively, it will emit the light emission. So light emission basically cover from the UV up to the IR part. Okay. So the basic principle which is governing this organic light emitting diodes is electroluminescence. So we are going to see what are the different type of emissive layers, what are the structure of these devices, and how the architecture is there in a top and bottom emission based OLED devices. Is it clear? Hello? Okay.
Yes.
So, of course, we have studied inorganic and organic electronics. We have seen many materials in a very basic sense, like inorganic, how we differentiate an inorganic and organic. So just on a textbook definition, organic materials are comprises carbon and hydrogen. Okay, it's a small molecules, or even sometimes it's a polymer. So basically, it's a chain of carbon and hydrogen. So you can see here I have given a basic methane, and you can see monomer is here. If the monomer content is called polymer, and when you see this, actually there are many good properties which you come across in your organic materials. But you see in a polyaniline, say for example, the electrical conductivity is 1 Siemens per centimeter. This is a very popular organic material which is given here. And after that, there are even several organic molecules from polyacetylene, PPP, PT, PPB, PPV. Like that, there are many organic materials which are used in different applications in our daily life. But when you see the organic electronics, it starts with a basic thing where your conductivity, many of the time you see it is the conducting, it's an insulating material. That's what we considered long time before actually where the Nobel Prize have been announced in 2000 for the development and discovery and development of conductive polymers for Alan Heger, Professor Shiragawa, and Alan McDermott. So in this research, they have shown acetylene, where the conductivity of 10 power minus 9, which means absolute insulators, 10 power minus 9 Siemens per centimeter, they have shown that it can conduct to 38 Siemens per centimeter. So there they actually started the groundwork for the conducting electronics or organic electronics. Actually we can simply classify into two different types of molecules based on their property. Broad classification say fluorescence and phosphorescence, which are the basic effects of light interaction with the organic molecule. Suppose if it emits light, okay, instantaneously, then that called fluorescence. Then there is a delay, and basically there is a interstate crossing. Then it is called phosphorescence material. Okay, so this is a basic thing in case of organic materials point of view. So what happened after the Nobel Prize? Professor Ching Tang, who is our scientific advisor, okay, so he came up with a concept of organic electroluminescent devices, which is organic light emitting diodes. This is the highly cited paper in the history. Okay, so this paper have been cited more than 15K. Okay, I think, and he came up with his colleague Stephen Wenslock. From both have been working for Eastman Kodak in Rochester. The paper is actually dealing with organic electroluminescent devices, okay, diodes. Actually, Ching Tang, when I had discussion with Ching Tang, he told me that the original invention was actually for organic PV cell, but they accidentally came up with organic electroluminescent diodes. Okay, this was the milestone in the OLED research. After that, the Professor Ching Tang, Stephen Wenslock, and of course our company CEO, Professor Dr. G. Rajeshwaran, both came from the lab to fab. So they established the first AMOLED commercial line in Japan, along with Sanyo and the Kodak. So it was a joint venture between Sanyo and Kodak. It's called SK Display. So they founded in Gifu, Japan, and they started actually doing AMOLED displays, which were used in Kodak cameras as well as for display, small displays, small medium displays. Okay, so this is how it came from the lab to the fab, to the manufacturing unit. So here I have given some of the broad timelines. What happened in 1963? The people came up with a light emission in Andrasin. When they applied 10 volt, they have seen the light emission. After that, in 1987, Ching Tang came with the two-layered OLED devices. 1990, first polymer OLED by Cambridge University. 2003, commercial OLED display by SK. 2009, thermally activated delayed fluorescent devices, Professor Adachi from Kyushu University. So these are the broad technology development happened in the. Thus, I'm moving into the second part of my presentation. Why organic LEDs? Okay, I've just given few examples. Why? Because the bonding which is present in organics are van der Waals bonds compared to the covalent or ionic present in the inorganic. So there are plenty of molecules available in organics. So you can easily tailor the molecules where you have phenols, ether, you have alkanes, you have nitro groups, benzene, aniline. So there are many variety of material present in the organic, so that the availability of material is not a problem. Simple processing, which means you can do a simple spin coating, and a quick lab proof of concept can be established. And you can do a low temperature processing. Okay, so you can simply go for a spin coating kind of thing, and you can establish a laboratory for a small devices. It's not for manufacturing, but for a proof of concept. Substrate selection. So no problem about the substrate selection. You can go for a flexible substrate like plastic, paper, cloth, or you can go for a rigid substrate like your ITO substrates, ITO class substrate. Okay. And you can directly integrate any of this AMOLED package into a lightweight kind of like straps. So that's where you came up with the wearable electronics, where nowadays you can see and everyone is wearing actually a smartwatch. So these smartwatch displays are basically from a AMOLED displays. So this AMOLED displays can be directly integrated in any of these wearable devices. Okay. What are the applications of organic material? Basically, organic materials are used in OLED. So we called LEDs, we call OLED. Organics are used in solar cells. So we call OPVs. Organics are used in lasers, organic lasers, used in memories, sensors, organic transistors, so on and so forth. So application of organic materials are as compared as good as your inorganic counterparts. Let us see the fundamental and mechanism of light emission. Okay, basically like how a typical energy diagram will be there on organic, inside organic LED. So I'm just given here the basic energy diagram. So the base of any organic LED is basically a glass substrate. On the glass substrate on the top, I basically have a anode for holes, which is anode, of course, for positive charges. Anode or this is basically ITO, and followed by hole injection layer, followed by a hole transport layer. The other side, I have cathode, either silver or aluminum, followed by electron injection layer, which is again any of the lithium compounds, lithium carbonate or lithium fluoride, followed by electron transport layer, and there is an organic emissive layer. So if you see, this is, I have here mapped this organic device, again their work function. So you can see anode, and you can see this is on the cathode side. Okay, this is on the EVAC and this is on the Fermi level. Okay, you can see typically the work functions and how this homos are arranged against the LUMO, and every time the holes and electrons will move towards your emissive layer and recombine at the emissive layer and produces exciton. Just on the lighter side, I have given OLED layers which are similar to a king size burger. Okay, you can see the anode is sitting here and followed by a hole injection layer, again hole transport layer, and you have a emissive layer, which is the big part of your meat on the center. Similarly, you have a cathode, electron injection layer, and electron transport layer. Okay, so the OLED layers are stacked in this way, where every time from the positive carriers move towards your emissive and electrons move from the cathode towards the emissive layer. What are the materials typically present in the OLED structure? If we see anode, as I mentioned, 95% people are using ITO, indium doped titanium oxide, because of the work function and other easiness. And few research have been done on using silver nanowires in place of ITO. Then the hole injection layer, traditionally people use Mali oxide, or HCN is a famous organic molecule, or PDOT-PSS, okay, where you can do the solution process. HTL, people typically use TPT, NPT kind of amine derivatives. And the active layer have been classified into three types: fluorescent based emitter, phosphorescence based emitter, and thermally activated delayed fluorescent based emitters. This is again species of fluorescence, but the mechanism is bit different, which I will cover in the coming slides. In the electron transport layer, people use BFEN, TBP, TACID, EAL, as I mentioned, lithium chelate or lithium carbonate or lithium fluoride. People use aluminum on the cathode, or magnesium silver, silver or silver aluminum. So these are the typical materials used in the OLED layers. What are the device architectures? Typically you can see either it is you can see the light emission coming from the bottom, so it is called the bottom emission, or the light emission coming from the top, which is called the top emissions. Okay, so simple difference is actually it is a light emission here. Actually, your encapsulation will be on the top, and the cathode need not to be transparent. So you can use aluminum or any material here. In case of top emission, light will come from your top. Say for example, your OLED TVs are bottom emission and your mobile phones are top emission. So you need a transparent cathode. That's why we are using silver or magnesium silver. Then you can put this structure in any one of the flexible devices. Okay, so that will become like a rollable or flexible OLED devices. Apart from bottom emission and top emission, you have transparent OLED. So light will come on the both the sides, where you can have your windows on a moving train, or kind of like a metro announcement, or those kind of things, or a billboard. All are basically on a transparent OLED. And sometimes you can have inverted OLEDs also. Okay, but typically, like as I mentioned, TVs are working with bottom, and mobiles are working with top emission. So what is the metrics which governs the characteristics, electrical characteristics of OLED devices? Basically, we say quantum efficiency. So quantum efficiency is nothing but the efficiency, internal quantum efficiency, and the outcoupling efficiency. So which I given that electron and hole injected, then they are recombining and producing exciton of singlet and exciton of triplet. And based on that, the singlet will go for a radiation. And again, triplet is also going for a non-radiative decay. And the radiation is out fully, okay, so which you see the emission which you are coming outside, which is called EQE, external quantum efficiency. Suppose it is vanishing inside, so you won't see any of these. So these parameters are called efficiency, external quantum efficiency. Apart from that, you have uh, means voltage, drive-in voltage, and you have current efficiency and color coordinates, CAE coordinates, XY coordinates, as well as lifetime of organic uh, light emitting diodes. These are the major typical parameters governing the organic light emitting diodes. Again, a small comparison between LCD, mini LED, OLED, and micro LED. So all LCD and mini LED are using a backlit display, not self-emissive, whereas organic and micro LEDs are self-emissive. And contrast are very high here. Response time is also very high because it is self-emissive. And only few issues, the technology maturity is now high, and the lifetime is not that much super here. You need to do an encapsulation. Okay, that's a major thing. Other than that, these displays are comparable with any of the LED or micro LED or mini LED. What will happen when you compare with the active matrix LCD? I'm here given the pros in green color and cons in the orange. So thickness is very thick. So I can say this is in micron level, very lighter. Unlike your LCDs, you can see a viewing angle of 180 degrees. You can reproduce any color. That's why people are going for OLED, because this color gamut is very good. Color reproduction is very good. Response times in nanoseconds, contrast ratios are high. Operating temperature as well as power consumption are less. On the con side, the diagonal, you cannot go for a bigger size, and like your LCDs. Lifetime, now it is in improvement stage. These organic molecules are coming out of a typical synthesis process, so that the raw material cost is higher. That's why it is expensive. Okay, other than that, the technology is fully matured. Let's see the organic materials and devices. Like I mentioned, the first generation is called fluorescence-based emitters. Second generations are called phosphorescence-based emitters, and third generation is called thermally activated delayed fluorescence-based emitters. So you can see in terms of cost, fluorescence are small molecules having very low cost. Phosphorescence, since it involves rare earth-based metals like platinum, iridium, and all, so it is high cost. And TADF involves no heavy metal, so it is low cost. What about the deep blue? Deep blue is a big problem, whether it is inorganic or organic electronics. The deep blues are available under development, but in phosphorescence it is unavailable. Color purity, high, and here it is low and low. But in terms of efficiency, fluorescence stands on the lower efficiency, where phosphorescence and TADF actually has a good efficiencies. What about the device configuration? As I mentioned, I am just compared the bottom and top emissions. Bottom emission, transparent substrate is required because light is coming from the bottom. Whereas in top emission, no restriction because light is going to come out from your top. Upper electrode, whether you can use a opaque based, aluminum based opaque. Okay, here it is should be a transparent like magnesium or silver. Encapsulation, it's easy, but encapsulation bit difficult here. People are going for, like I mentioned, for TV sets, bottom emission and mobile top. What about the aperture ratio? Here very low because you need to match this with the LTPS circuit on the bottom, whereas here it is high. Lifetime, short, medium. High resolution, it's not possible because again light is coming from the bottom, whereas here it is possible. Again, as I mentioned, what is the quantum efficiency? Quantum efficiency, the formula is how many number of electrons, photons are emitted to the ratio of recombination of electrons and holes. Again, the external quantum efficiency is the product of internal quantum efficiency and the extraction efficiency. The external quantum efficiency is maximum for red and near close to 19 in green and very less for the blue. So this is basically the CIE diagram where you taken care of the colors which you can reproduce from any of these X and Y coordinates. Just brief description about our work. So the ARC Center, AMOLED Research Center in IIT Madras, where we do OLED deposition and encapsulation. These are the major work which we are having. This is the view of our class 1000 clean rooms where we are having vacuum thermal evaporation and encapsulation setup. And we use LTPS based TFT substrate for the OLED deposition. And we do even without TFT also for the pilot demonstration. And after that, we do the encapsulation and we can fabricate as a display module. So here I have given that some of the devices fabricated from our lab. So you can see this is a full 6-inch device. Out of that, I have given you the 4 pixels. Okay, so you can see the IV as well as this EQE diagram for our blue. So you can see this blue turn on voltage is less than 2.6, and driving happening here, which is about 3.4. This is this is near to a current efficiency of 10.4. Okay, and the color coordinates are 0.13 and 0.14. It's of course close to deep blue. If you go to less than 0.1, then it is a deep blue. So on the quantum efficiency of 10% and the full width maximum is 50. Okay, so the narrow the full width up maximum, the deeper the color. Similarly for the green OLED devices, where the structure is given here. So we use ITO, HCN, HTL, and we use aluminum, lithium chelate, and ETM doped with lithium chelate and molecule from Merck for the emissive layer. So again, the same principle, and the green light emission is shown here. Similarly for the red, so here you use 2 systems. One is the host, another one is co-host system for the electrical activation. So you can see here the red, and the characteristics is 0.69 and 30, and a current efficiency of 9 candela per amps, and a quantum efficiency of more than 15%. How the OLED fabrication process is happening? People are using vacuum thermal evaporation, sputtering, spin coating, inkjet printing, screen printing, and laser induced thermal imaging kind of process. Okay. So basically, like I mentioned, we typically use a vacuum thermal evaporation where you can use a crucible filled with organic molecule, and when we apply the current, and the thermal evaporation will happen, and the substrate is on the top. And using a shadow mask, you will deposit between this shadow mask and wherever you want the pattern, that particular material will be deposited. And the thickness is monitored by a QCM, crystal monitor. So this is the facility which is used in our center. So use full vacuum thermal evaporation. Similarly, you can do a physical vapor deposition called sputtering. Advantages, you will have a good dopant control. You have a control over your temperature and carrier gas flow. And this is suitable for large area application, which I have given here. And this is a heat-based method, so growth of dense film is a bit challenging. Spin coating again is a very simple and cost-effective process, which is used for proof of concept and lab, and suitable for soluble conjugated polymers. And just to check, just dispense the polymer solution, rings, ramp up and dry, and you will get a simple device. And of course, you need to make out your contacts. Inkjet printing, again, you convert your organics into inks and just drop this ink, and no need for masking process. And it is suitable for large area display applications, but the display quality is not that equal. This is used for billboard and other application. You have a very good manufacturing flexibility, but the challenges is the ink rheology is very important, because the rheology will change during your drying and evaporation. What is the kind of displays? Okay, typically if you see, we have glasses starting from generation 1 to generation 10, where you coat organic light emitting diodes. So typically generation 10 means, you see in this actually 28, 32 inch TV panel can be manufactured. Here if you do 42 inch TV, then 15 panels can be manufactured. And if you do actually a 65 inch in a Gen 10 display, you can deposit actually 65 inch TV. So here I have given from generation 1 to generation 10. So of course now generation 10.5 is in progress. So this is a typical process flow of red, green, blue side by side AMOLED. So typically the ALOD evaporation is one cluster and OLED encapsulation is one cluster. So you bake and clean your TFT thin film transistor substrate, do a O2 plasma, deposit whole injection layer, whole transport layer, and individually you do a emissive red, emissive green layer, emissive blue layer. Then again you deposit ETL layer, EAL layer, and cathode, and you put a capping layer to avoid any oxidation. Then this will be transferred to the OLED encapsulation, where you do a laser-based curing, means this is a laser-based process. After that, you attach a cover glass. Basically, cover glass is to avoid any kind of oxidation or any moisture ingress to the substrate. So after that, it will go for inspection, curing, then you cut and check on the light. Okay, this is the process flow of side by side. So this is how in industry, like industry follow a cluster type. Backplane will be introduced, and in one cluster you have HIL 1, 2, 3, and again you use plasma in some places for cleaning. The cassette will again come from here. Again you do a blue first, followed by red and green. Then you do a cathode and it will go for your encapsulation. So your structure will look like this. How do you do encapsulation? Basically encapsulation where you will attach a cover glass on the top of your device glass. Like I mentioned, the purpose is to avoid any type of moisture ingress and oxidation, because organic devices are very sensitive towards oxidation and moisture. Any moisture ingress and any oxidation will kill the device. So where you will get a dark spots. So this is a typical comparison of red, green, blue side by side. Similarly, you can use white light and you can produce the other colors. So here you can produce high performance OLED devices, and this technology is a fine metal mask based technology and used in mobile devices. As I mentioned, this is a top-up display, and here white light is very good for TV, OLED TV, and where light is produced on the bottom. I've just given a simple comparison of SD, Samsung display, and AU Taiwan. So both are like, this is side by side and this is white OLED based TV display. This 4.65 and 4.4 inch. You can see the panel brightness is 240 candela per meter square. The similar, the NTSC standard is more than 100% in both the cases, and power consumption here is 434 milliwatt, and this is mini 300 milliwatt. Okay. So let me just take another 2 to 3 minutes to brief about challenges and opportunities. The burn-in effect after long time of usage. So you will get a burn-in kind of effect in your self-emissive based organic displays. Because of this burn-in effect, you will get an image sticking. So you can see here, this is 0 hours. You look bright, and slowly after 1000 hours, after 2500 hours and 5000 hours, you can see the image is turning into gray. This is because of image sticking or the burn-in effect. OLED degradation, as I mentioned. So when you use this for a longer period of time, because of moisture and other problem, the degradation will taken. Here I have given in horizontal axis time and vertical axis lumens. So you can see actually the first one, the logo. The logo degradation is very fast, and you can see this background degradation is slow. So you will get multiple OLED degradation profile. The degradation mechanism is a complex one. It's very difficult to understand because it's not a single mechanism, it's a multiple mechanisms where you will get a photo-induced reactions between your different materials, metals, metal migration, diffusion migration, morphological changes in the organic, temperature increases in the surroundings, delamination, impurity-based quenching, so on and so forth. So because of that, the degradation is very rapidly occurring in the organic devices. These are the major challenges. Lifespan of a blue LED is 14K hours. When you switch on your TV and put only blue then the TV will close within 15K hours. Fabrication cost is, again, of course, as I mentioned, it's a high-tech manufacturing process. Talk time is also is high. So the fabrication is quite challenging. Like I mentioned, the degradation, the reaction happening at the electrode and the organic interfaces, water vapor transmission rate, moisture ingress are the reason for the degradation. Scaling is quite difficult because it's not quite simple like your inorganics. Efficacy, lifetime, color uniformity, and a larger area is quite difficult to achieve. The scaling process is also a bit difficult in OLED, unlike your LCDs. Of course, competition point of view, there are multiple technologies are coming like quantum dots, several nano dots, several things. Cost and reliability need to be checked in this kind of based devices. So to sum up that, what are the basic applications? The OLEDs are used, organic light emitting diodes are used in mobile displays, head-on displays, automotive tail lamps, TVs, AR, VR, augmented reality, virtual reality, lighting, so on and so forth. There are here I have given different companies involved in different process. Say for some of them are Canon, AICTE, Hyundai, 3M, Sharp, Samsung. These are the companies in the OLED preparation. OLED manufacturing in India, there are two major centers. One is Department of Electrical Engineering in IIT Madras. Of course, this is on the OLED devices. I'm not talking about the material. And Center for Flexible Electronics in IIT Kanpur. This is a final slide of my presentation. So I hope I have covered basically like what is organic electronics and why it is used and how the organic electronics is functioning. The design and working of organic light emitting diodes based materials and devices. And finally, like the methods used in organic light emitting diodes based devices, the pros and cons. How to get a low cost display at the better lifetime is the challenging task. Okay, so to conclude this, the take home message is the organic light emitting display era is here, and you can use either foldable, flexible, rollable devices for a better usage of your devices. Few references I have given. So this is a Society for Information Display based publication, Organic Light Emitting Diode based Display and Fundamentals by the SID chairman Sujimura. Organic light emitting based diodes by Buckley. And this is not only for organic, this is for LCD, covering LCD micro displays and other. This is Handbook of Visual Display Technology. You can visit this basic displaymate.com. This is if you are a maniac of mobile phones, you can check this website. So every time any new phones are coming in the market, so he will buy the phone and he will check the display and publish the review of the display. And OLED Info is a basic website which will give you information about your displays. And finally, thanks for your patient listening. And if you have any questions, please let me know. Thank you.
Hello.
Hello.
Yes, sir. Yeah. So thank you for the very nice presentation, sir. This is Nagarajan here. Yeah. Thank you so much for accepting our invitation also. So now it's open for discussion. So any questions?
Hello.
Yes.
Some of the white LED bulbs are likely to cause some neurological problems. I want to know what is the selection, any parameters you have to check. Anything on that, can you?
Sorry, sir, this topic is very new to me. So this white LEDs are, you have two type of display, basically cool and warm displays. But I am sorry, I really don't know about this creating health issues by white LED light.
Some derived from blue LEDs, white light derivation causes some neurological problems. That it was
actually in the other way around. The one which I have shown, the near infrared based displays are curing autism related problems. That I am aware of that. Okay, because these single wavelength near IR emitters are good for concentration. So people are using this low light based therapies to cure these kind of devices.
So OLEDs can overcome this? No, nothing.
Yes. OLEDs are people are working in different part of the world, especially in South Korea. People are working on the curing of this autism related problems using near infrared emitters.
Okay, thank you.
Sir, it's a really good presentation. Sir, if any inorganic material could be used for light emitting device applications, because some compounds, inorganic compounds also near NIR active compounds also there. No?
Okay. So you are referring to phosphors or you are referring to NIR semiconductors, IR semiconductors?
Thank you, sir.
Dr. Rajkumar, your question is on phosphor or your question is on inorganic semiconductors?
No, sir. Any inorganic material could be used for your especially organic item.
Exactly. So that's why I have shown the comparison. I'm not comparing this light emitting diodes along with gallium nitride and gallium arsenide related material, because the application here is totally different. Okay. So here, like I mentioned, you cannot derive any of this, fabricate this any of this material on what you call this foldable or flexible substrates. So organic is mainly meant for foldable and flexible substrates. So inorganic, it will be difficult to deposit on a flexible substrates. So that's the main thing. And of course, as I mentioned, the other advantages and other basic things are there. Yeah.
Thank you, sir. Thank you so much.
Sir, very nice informative session, sir. Thank you for your excellent presentation. Sir, my question is, sir, organometallic compounds where that homo-lumo transition will be facile compared to pure organic compounds.
Yeah.
So organometallic compounds can be incorporated in OLED, sir?
100%. So this organometallic, the metallic part, can you elaborate on that? Okay. Are you talking about heavy metals?
Not really heavy metals, sir. Iron.
Okay. So basically, like this again, the emissive part, which I have shown 3 different classifications. Okay. So the first classification based on fluorescence, which are small molecules. Okay. And the phosphorescence is based on heavy molecules. Okay. So the TADF derivative, which I have shown, it's actually is organometallic compounds. Okay. Unlike your noble metals. Okay. Plus, it's not a fully a iron, it is also like other metals also, including other metals also. That's why it's mainly on thermally activated and delayed fluorescence, where you are making use of your singlet as well as your triplet excitons. Yes, it is possible.
Thank you, sir.
I hope there are no more questions. I would like to thank Dr. R. Bairava Ganesh, Head Cell Process, Tata Power Solar Limited, Tirunelveli, for his talk on AMOLED displays.
Thank you. Thank you very much.
Thank you, sir. Thank you so much. Thank you, sir.
Thank you. Bye.
The final session is handled by Professor Deepak Kumar Goswami from Organic Electronics Laboratory, Department of Physics, IIT Kharagpur. Professor Deepak Kumar Goswami completed his bachelor's from Kamarpukur SRS Vidya Mahapit, West Bengal, and his master's from Burdwan University, West Bengal. He received his PhD from Institute of Physics, Bhubaneswar, and worked as postdoctoral research fellow at Northwestern University, Material Science and Engineering Department, USA, and at Max Planck Institute for Metals Research, Germany. After that, he joined as an assistant professor at IIT Guwahati, as an associate professor at IIT Guwahati and IIT Kharagpur. At present, he is working as a professor at Department of Physics, IIT Kharagpur. He also served as a visiting scientist at European Synchrotron Radiation Facility at Beamline ID32 and Surface Characterization Laboratory, France. Apart from his academic positions, he also worked as a guest editor for Advanced Nanomaterials and Nanotechnology, Journal of Experimental Nanoscience, International Journal of Nanoscience, and AIP Proceedings. His research interests include flexible and stretchable organic electronic devices, organic field effect transistors, bioelectronic devices, affordable healthcare devices, surfaces, interface, and nanoscale sciences, X-ray physics, and ion-solid interacts. We are profoundly grateful to have you here, sir. Over to you.
Yeah, so am I audible?
Yes, sir.
Yeah, okay.
Audible, sir.
Thank you so much.
You're audible.
Yeah, thank you so much for kind introduction, and also I thank the organizer for giving me opportunity to talk about some of the works that we have been doing for past decade. And of course, it is wonderful program. So let me share my screen. Okay. Entire screen. Excuse me. Is my screen visible?
Yes, sir.
Yeah, okay, fine. Yes,
Yeah,
so
it's fine, sir.
okay, good. Yeah, so it's a wonderful, I think, program. I have given talk to many faculty development initiative program, but this one is very specific on organic semiconductor innovation. And as you have been hearing lots of talks, I think last few days on these materials, and you could actually understood that the potential of these materials and the related devices in coming decades. So what I plan today is talk about flexible organic electronic devices for a very specific application called wearable healthcare. And the things like I'll take you through the journey that we had for the last several years in the lab, where we actually do very fundamental research to a development of technology, and push it to a product as which will be perhaps will be available in the market. So that's would be an interesting journey for you also to hear, because being academicians, we mostly focus on the fundamental research and developing some of the proof of the concepts in the lab, and we publish paper, and at times we patent things. But I think what is very critical at this point of time in our country is essentially to bridge the academic institutes to industry, because the requirement of the industry and the kind of things, kind of innovation that we do at the lab are absolutely different thing. So what industry requires, we don't really develop in the lab. So this is the journey that I'll take you through, at least in the first part of the talk, that how we started from very material level research to a development of a product, which is a medical device, and how we can validate it, and at which level you can actually translate it into a technology which will be useful to the people of the country. So let me go with that. Since we'll be talking about flexible device, so if you think about flexibility, the highest level of flexibility that we have, is the imagination. Like you can close your eyes and think that you are in Mars, right? There's no issue on that. So it's absolutely, flexible, my imagination, and it has no limit. And, you can think of anything. And the important thing is that when when we talk about even the flexibility of electronic devices, then again, first thing that came is the imagination that there can be some organic materials, organic polymer, which are conducting, which can even conduct, electrons. So that was discovered a long time back, and led to think that one can think of using this material for developing really some of the flexible device. So as it says that in case of flexible electronics, you still need to imagine, and I think it's quite some time back in 2008. It's a very well-known scientist. He in fact demonstrated. He talked about some of the flexible devices. It's actually Jinan Bao from Stanford University. He developed transistor using carbon nanotubes, right? So these devices were flexible, and it leads to some kind of flexible application also. But what this paper actually, become interesting to me is the title, which is says that stretching our imagination. And what I said in case of, imagination is something that has no limit, and it's absolutely flexible in nature. So to in fact develop something in coming days, just to motivate a little bit to the students that and the teachers, of course. That unless we imagine something, we cannot make it in reality. So first step is that you have to be really imaginative and innovative in mind. So when you talk about flexible electronic devices, there are many such fancy eye-catching devices are already in the market, and I'm very sure many of us actually use everyday life, like flexible display LED, right? So these are all devices. Mostly they are flexible in nature, and you see some of the application. But what we as a scientist working in the flexible electronics decided that this field, what you see here is very competitive, and kind of infrastructure that you need to really compete with the companies and the innovation that they made, like Samsung and other. Definitely the kind of academic institutes that we have in our country do not have such facility. So we really need to think different ways that we exploit these devices. And what we started thinking is that why not to use these flexible devices to healthcare. And it's very important for a country like us, where we have so many people and so less healthcare facility, including doctors, hospitals, caregiver, right? So of course this is the area that maybe we can contribute. And some of the flexible device which you see here actually are developed in our lab, and I'll show you some of the technology that also we developed. Now, just to have a little bit more motivation to think that why not to work in this field, if you look at the global wearable medical device market, right, which are basically comes under three categories: sports and fitness, remote patient monitoring, and home healthcare. Sports and fitness, of course, we still use wearable device. I'm very sure many of us are still using, like at current time, which are mainly the smart watch, right? So it comes with many sensors, and it actually counts your number of steps for whole day, how much energy that you have burned, and what is your heart rate, heartbeat. So all sort of parameters which are very important to know your well-being, to actually take to track these parameters through this device. But what is again the important is for us is home healthcare, like, since we don't have many facilities in our country. So if we can develop some device utilizing this technology, flexible electronic technology, and make some affordable healthcare device which can use everybody, would be really interesting and effective for us to do. So what is this market? Is you see the basically the growth, something like 26% forecast, and it's a huge market that we have. Mostly this prediction is like diagnostic device and therapeutic device, right? So these are all wearable device, and this is only the forecast in US. Now you can see that country like us, it will be even more, right? Because our requirement is very high. So this is again another prediction. It says, this almost like 20 billion US dollar is some revenue, annual revenue generation. And what you see here is essentially different types of wearable technology, right, which is necessary to do that. So those who are thinking of working and taking their career to this kind of research direction, I'm very sure you can get enough motivation that not only to do fundamental research and technology development, but it has a huge market and there will be a lot of revenue generation if one can do that. So when you talk about the wearable device, then the first thing that comes to all of your mind is something called IoT-based device. What is IoT? It's called Internet of Things, right? So Internet of Things means like you have a cloud, you have a central part of a full ecosystem where we have many things that we do every day in our life, right? So like something like smart retail, smart homes, wireless connection, embedded system, IoT in healthcare. So all these things essentially what we do every day are connected to a cloud, and from your home you can actually get access to everything through this cloud server. So that is called Internet of Things. But when we talk about medical device, we also have something called Internet of Medical Things. And what you have in this Internet of Medical Things is all these stakeholder of medical fraternity, like primary care giver, emergency service, home health care, secondary caregivers, right? And then there are emergency service available. So all this thing, if we can connect to a same cloud, cloud, then you have access to your fingerprint to all these facilities. Now, what you need is another part to integrate in this Internet of Medical Thing is like some of the wearable, affordable, and smart medical device which can be connected to all the time to you and can give feedback to all the stakeholder wherever it's required, and they can even get to know if you are in trouble or if you need emergency service. So this is what is the whole, circuit or internet that we are talking about, and this requires development of a lot of healthcare sensor, which in fact we have taken up some of them, and develop some of the technology which will be connected to a cloud server through your mobile app, and anybody even from anywhere in the world also can look at your health performance. All right. So before I move, so let me just also tell that if there is a signal problem, a connection problem, maybe I'm not able to see the back screen. So if you don't hear me, just please knock me my mobile phone if I lose connection, such that you understand what is going on here. So let me continue. What you see is there are lots of healthcare devices, right? sensors, and they are categorized in 4 different categories like temperature sensor, pressure sensor, sensor in the integrated platforms, and strain sensor. So these are 4 verticals, and under these 4 verticals we have multiple sensors like body temperature mapping sensor, wound healing monitoring sensor, health and pulse monitoring system, voice monitoring system. So these are many, as you can see that the things are listed here. All this sensor one has to develop and integrate into a kind of prototype module and make a medical device and connect into the rate of medical things. Then, of course, we can actually have a lot of flexibility in giving healthcare support to the people of the country. And all this star that you see, actually, all the sensors, we actually developed in our lab, and I'll talk some of them depending on the time, and I'll also so that there are enormous possibilities like world of opportunity on flexible electronic device in healthcare itself, and then one can take through this topic in their career. So the first sensor that I'll be talking about is temperature sensor, and this is ultra fast and ultra precision. So ultra fast, like it takes a millisecond time to measure your temperature, and ultra precision is milli up to millikelvin temperature it can measure. And what is the material that we use is basically barium titanate nanocrystal and some other polymer along with that. And we actually made medical device like monitoring body temperature, continuous monitoring of body temperature. And then we also have developed a smart mask which is useful for sleep apnea, and another smart spirometer which is called chronic obstructive pulmonary dysfunction related disease, COPD, asthma, such thing to detect and monitor. Second sensor is the humidity sensor. In this humidity sensor, we used sensing material like proteins, like gelatin and albumin. And also this humidity sensors also can be used for different medical applications. Next one is the strain sensor. The strain sensor is basically the pressure sensor, and we made it with silver nanowires, and it can it's extremely sensitive sensor. It can measure heart rate and also blood pulse rate in your artery very comfortably with high precision. Next sensors, types of sensors that we work is different type of biosensors, and this includes HSA protein detection, and then in fact we also developed a COVID detection sensor during the COVID lockdown period, and we demonstrated that they work. And nevertheless, we also have some kind of UV sensors for skin disease detection. We have self-powered flexible devices which are protein-based, which actually it's basically a self-powered device. It doesn't need power. It can generate power and now can be operated. And of course, the last one which we recently started working on is a synaptic device. These synaptic devices are essentially for healthcare application, biological applications. So there are many papers and patents that we actually publish out of this work from particularly in the domain of sensors. So first one, as I mentioned, that the temperature sensor, and what we developed, there are 2 medical device. One is called a spirometer. So this, as you can see, it's a handheld device. It has a sensor in it, inside it. I'll show you later. And this is the smart mask, and this is the sensor. So this one actually is developed for chronic obstructive pulmonary dysfunction disease, COPD, and this mask is essentially for sleep apnea and even emergency medical service EMS. So we not only develop the sensor, but we also develop the electronics. You can see that it's like a coin-size electronics developed, which can go comfortably with any small handheld machine and a device. And what you see here is there is a Bluetooth connection. So it collect data from the device and transfer the data to an app, Android app through this Bluetooth connection. So this all component that we develop in the lab. Cell power device, you can see these are actually ultra flexible, so it's developed on the 300 micron page substrate. And as I mentioned, it's a cell power, it absorbs humidity from ambience and it generates power. At the same time, it can also work as a sensor. So this is mainly the sensitive material is actually protein. And we also demonstrated that this, as you see, that it's really ultra flexible sensor, and it can very comfortably measure the moisture concentration to any of the area where you have wound. And the monitoring moisture concentration in the wound area is very important for the doctors continuously monitoring to monitor the wound healing mechanism. Because if it is completely dry or fully wet, so both the things are actually not good for healing. So there is some kind of percentage of relative humidity should be maintained, and accordingly the treatment is decided. So it is very important for monitoring this wound healing moisture concentration during wound area. Next sensor, as I already mentioned, that during the COVID time, we developed a sensor, which is organic field effect transistor based sensor, and we demonstrated that it can detect COVID virus. COVID virus from saliva samples. It doesn't need to collect data from nasopharyngeal sample, because it's very sometimes difficult. And just it can be used for self-test, and it takes only minute time to detect whether your saliva has virus or not. So you can see that we have app, and this is the profile of detection. So it's like only few second time, it can tell you whether you have a COVID positive or COVID negative. The strain sensor that we developed, which you already see, is mainly based on silver nanowires, and you look at this profile. If you mount it in your artery, then this kink that you see here in the profile is basically blood pulse wave, which is passing through your artery. And this kink that you see are essentially telling you how the valves in your heart actually are closing and opening. So when it's closed, it puts a pulse on the blood, and that pressure a little bit increases, and you can actually see the shape of this blood pulse wave in your artery. Now this is very important because the shape of this pulse wave for you and me are different, because our valves are operating in different way. And just by analyzing the shape of this pulse wave, there are a lot of critical healthcare problem can be identified very easily through this, which some of them I'm going to talk. The next one is, in fact, the last kind of device that I'm going to talk, of course, depending on the time. That is called the synaptic device. And synaptic device, you must have already heard about it. But what I'm talking about, not for neuromorphic computation, but it's for the real biological synapse that normally we have between two neurons. Like, this is one neuron, this is second neuron. And between these two neurons, actually, there is a synapse. And the signal, passing through this nerves to neurons to neuron through this synaptic component here. So if you look at this, the way this works is essentially there are lots of ions, and when there is a signal, like let's say I touch on my body, so my brain recognizes that something touched on my skin. So there is a signal passes through my finger to the brain, and brain immediately decided that there is something actually in contact with the skin. So how first you can imagine, right? So essentially brains, there is a signal passes through this synapse, And this is sort of like a small neurons connected to brain, and it's tremendous fast. So what you see in this, what is the function of synapse is like transferring signal from one neuron to another neuron. And why do we need this kind of connection? Like why not like just one whole neuron from connected from the finger to our brain? Because that may not be very efficient. So you need to have a small neurons, and you should have some kind of synaptic device which actually kind of like an amplifier. So it transfer this, not only transfer the signal, but also it's amplify the signal a little bit. So which you normally see like when you have the cable connection, like cable lines which are coming from home to home, right? You see there is a kind of small box hanging, so that's basically the amplifier. So it's amplify the signal and such that you get a better signal at your home. So this synapse also does the similar thing. Not only the transfer the signal, but also a little bit amplification and stuff. So since there is a ion conducts this signal, so you can think of that one can have a electronic device where actually the charge transfer. So we in fact develop these devices with different kind of materials. Mainly these are all bio materials and biocompatible materials for different applications. So let me start with in the first part. It's basically from fundamentals to technology development. If you just think of, and just quickly go through that. This is right that you take a material, right? And if you take a material, then if you we think about the charge transfer through this material, then we essentially consider the electrons, right? And if you take, let's say, silver or gold or silicon, so what you see is this atomic number actually tells you that how many electrons that you have in a single atom. Now you can think of that if I have a piece of material, let's say I have a piece of gold material or silicon material, which is semiconductor. So I have billions of atoms, and I can have, let's say I have, if you think about, let's say I have 10,000 atoms in a small piece of silicon material. I have 10,000 into 14, that many electrons which I have in that material. Now, where are those electrons? So not only like look at the atomic structure, but what is happening is this like periodic arrangement of the atom, which leads to a formation of band structure. And in this band structure, there are two bands for the material. There is one band which is filled, another band is empty. So in these bands are essentially energy levels, and there is a gap between this empty and filled state. And the filled state is all this like 10,000 times 14 number of electrons are here, but there are some other energy levels which are free. So you can think of, so now we, of course, we have different types of material depending on how this empty state and filled states are there. So depending on this arrangement of electron in the material on their energy levels, and now we have three different types of material: conductor, semiconductor, and insulator. And depending on the gap between empty and filled state, we categorize them like metal, there is no gap. And semiconductor, you have a gap between 2 to 3 electron volt, and if we have insulator, then the gap is really high, which is greater than 3 electron volt. So if you think about that, if I take a material, something like this, and then I make 2 contacts, and then I connect with the battery, how does this electron flow? So you think about when I have a piece of material like having 10,000 into silicon atom, right? So that many electrons I already have in the system. Now when I connect to a battery, then basically I transfer additional electron through the contact to the material. Now this material, whatever electron, let's say 10 electron I transfer from battery to the material, this 10 electron has to be first accommodated into this material. And where do they get accommodated? Because not in the filled state, they should be accommodated somewhere in the empty state. And if they are accommodated, then only I can collect them at the other end. I have a complete circuit of flow of electron, which can actually give me charge flow and current. So now if I have metal, then of course there is no gap, so you can very easily transfer electrons. If you have a semiconductor, you need to put a little bit of voltage such that you can push electron from here to here, And if you have a really big gap, then you cannot even push electron, whatever, like very high voltage. So high voltage is essentially the electric field that you give between these two contacts, which is like if you put V voltage, then the electric field that you generate is V by D. So that electric field actually drives the electron from one end to another end, and you get a kind of like a current through that. So for insulator, you cannot flow this current because the gap is very high, but semiconductor, you can gap fill because the gap is small. You need little bit voltage and little bit electric field to push the electron there. So this is how the materials are categorized. What I'm going to give you some very quick description of that how charge flows through this device. Let's say I have a semiconductor connected by two contacts. So if you look at this energy band diagram, then basically I have valence band and conduction band, or valence band and conduction band. These two are basically two metal contacts, so there is no gap. Now if I have a semiconductor in between, right, so then I have density of state. So density of state for the semiconductor, I have field state and I have empty state. So this is conduction band, this is valence band. Now, if you connect them with the battery, then what you see is, let's say there is no battery and just connect them. So then this energy levels, like up to energy level up to which all the electrons are filled, all energy levels are filled, is called Fermi energy. So up to this, the electrons are filled in these two contacts. So, and in the between, then you see that there is a gap, so there is no energy level here. So this electron cannot go to here, right? Because there is no energy level which can conduct. So it's sort of like a kind of connecting highway between these two contacts through the semiconductor. So if there is no highway, of course, the electron that you transfer from here to here cannot go there. So all you need to do is that you need to, you don't have any current flow in this case. But if you apply some voltage, then let's say I applied negative voltage in this contact. So and push, let's say some transfer 10 electrons here. So if I transfer 10 electrons, so let me take the pen. So if I transfer 10 electron here, right, 10 electron here, so this 10 energy, less 5 energy level here will be occupied by the electrons. So I push this Fermi level going up in this direction, and I take some of this electron out in this direction, and I open a gap between this and these two contacts. Now you see within these two contacts, when I open up this gap, then I have some of this energy level in the conduction band which are between these two contacts. So I have kind of like window, and this electron can actually go through this, taking this energy level to this valence band. So I can have a kind of energy charge transfer through this device, through a semiconductor layer. So this is very important, and one can actually write down the current flow very easily. So looking at the density of state here, and this is actually Fermi energy difference, and you can write down D into Fe into D. So that gives you the total charge transfer, and the total current should be like I naught, which is Q gamma by 2 H cross. So gamma is essentially charge transfer, how easily you can transfer electron from here to here, and how easily you can take electron from here to here. So this is gamma 1 and gamma 2. This is gamma 1 and gamma 2. So this is essentially the current, and you understand that how actually current flow. Now all the device that I'm going to talk about is using different type of materials, and they have different energy band diagram. Exploit that energy band diagram to understand the charge flow, and once you understand the charge flow, then you understand where these devices can be used for what purpose. That's very important to have understanding for that. Okay, just so what is the device that we actually are using? So that's called the organic field effect transistor. So organic field effect transistor, and what you know here is that we have a gate, we have an insulator, we have organic semiconductor layer, and then source and drain. And when you apply some voltage between source and drain here, so there is a current flow, charge flow, in fact, from source to drain. And at the same time, when you apply the gate voltage, then you know that I have a kind of electric field that I develop, which is V by D, right, which I already mentioned. And this electric field actually induces charges at the interface here, and this charge can actually control the current flow between source and drain. So this is that function of gate. Like gate is kind of like function that control the charge flow from source to drain. That is what called the transistor. So if you want to develop a transistor, then of course what is important is that you need all type of material. Let's say I have a conductors, right? I have a conductor, I have a dielectric insulator, I have a semiconductor, I have a conductor. So all three types of materials that you need, and then you develop a very ultra thin film and put them together in this fashion, then you have a transistor. So this is how exactly you develop transistor. And then whether these devices will be flexible or stretchable or not, that depending on the selection of this material that you have here. All right. So if the materials are not flexible, your device will not be flexible. If your materials are flexible in nature, then device can be flexible, including the substrate, which also has to be flexible in nature. All right. So how do you use this device as a sensor? So organic feedback transistor is an electronic device which can be used as a sensor. How do you do that? So there is a very fundamental understanding of making the selection of material for a specific application. For example, in this case, we consider the dipoles, and the dipoles are essentially separation of charge, like negative and positive charge, which is P, and can be written like Q into D, right? And when you apply some electric field in this kind of dipole, then basically there is a force which is applied here, right? And negative force is applied there, so that force is basically Q into E. And so your basically dipole get kind of like a torque, and because of the torque, this dipole get polarized. And when this dipole get polarized, so this is your electric field direction. It try to get polarized along this. So the PD, you get a component along the PZ direction. And if you can find out the PZ components of, so that's the polarization of the electric dipoles. So if you can polarize them, then the things that is changing is basically epsilon r. Epsilon r is the dielectric constant. So this is classic Clausius-Cosoti relation for dielectric constant. If you can make a little bit change in polarization, Z component of the polarization vector, then you see that your dielectric constant will change, and this is actually goes to square of that. That means little bit change can make significant change in the dielectric constant. And if you can make this dielectric constant different, by some reason, let's say I'm hitting the material up, and when I hit the material, its polarization is changing, and if polarization change, dielectric constant changing, and if dielectric constant change, then my accumulation in the charge semiconductor layer is changing, so my current flowing through the device is changing. So I can, in a way, sense temperature in it. So that's very easy, process that we want to implement here. So for example, I can use this insulated layer. In fact, I can use any of this semiconductor insulator layer as my sensing layer. So if I want to use insulator layer, I can select a material having permanent, electric dipole moment in it. Most of the organic polymers, it has dipole, different kind of polar group connected to the dipoles, and they are actually acts like electric dipole moment, right? So when you actually apply electric getting polarized along here, and because of that, can actually, induce lots of charges. It's like a capacitor, right? So if you put some kind of here, then you induce positives. If you put positive charge here, induce negative charge there. So you basically accumulate charges, and that can change the current flow through this, and you can actually sense the reason which actually change the depolarization of the dipole moments that you have. So this is as simple as it is. Now let us take an example. For example, barium titanide, right? So barium titanide is a very, well-known material. There are a lot of studies have been done on this material, and what you see is the interesting property of barium titanide. If you look at the variation of dielectric constant epsilon r with temperature, you see there is a structural transition, like structural from rhombohedral to orthorhombic to tetragonal to cubic. So these are all structural transition happens at different temperature. And when there is a structural transition, if you look at the epsilon r, you see the epsilon r is also changing, like going like this, then there is a jump, and going like this, again there is a jump. So you think that this parameter is very sensitive to temperature for this material. So we had taken this material as a temperature sensitive material because it has a, during the room temperature, not the room temperature, in fact body temperature region somewhere here, it has like linear variation of the dielectric constant. So if we can use this material and heat up, then I see the dielectric constant changing. If dielectric constant change, then definitely my source to drain current is going to change because of the accumulation effect. So I should be able to sense temperature in a way. And this is what we all did. And you see that we actually made a barium titanium layer here in the insulator layer. And you see when we actually changing temperature, the capacitor of this gate, right? Gate capacitor. So this is a capacitor. The capacitor is linearly increasing. And also if you look at the source to drain current, which is also linearly changing, and get a calibration curve, like at any temperature if I heat, I know how much will be my current, then I can measure what is the current. Or in other way, if I measure some current in the device by varying temperature, I can immediately tell what is the temperature there. And this value like 80 nanoampere per degree centigrade is very high value of current, which can give you the resolution to millikelvin temperature range, and the response time is also pretty fast. So these are all material characterization. I will not spend too much of time in it, but what you see here, that once you fabricate this device, then look at the carrier mobility of this transistor, and we in fact check, this is in days, so we checked in fact over a year time, and how the carrier mobility is changing. And we do see something like, it does degrade, but at some point, like when your carrier mobility is something like 0.2, it's almost like a flat, right? So this is saturated at somewhere carrier 2. So if you use this transistor, so as a temperature sensor, it can go for years time, so without changing its property significantly. So that's the stability. So I'll just, this is the transfer characteristics, output characteristics of the transistor, and you see that this is basically the flexible transistor, right? And we check the flexibility also. This transistor are fully flexible up to 4 millimeter bending radius. Then after that, of course, it actually property changes, but that's like in up to 2 millimeter bending radius. But the 2 millimeter bending radius is very small for some of the application that we do for healthcare application, because our body undulation is not like having like 2 millimeter diameter bending radius. So naturally, all these devices up to 4 millimeter bending radius are absolutely fine. All right. So just to confirm, can you hear me clearly, or there is still issue? Any issue?
So no issue, sir. It's perfect, sir.
Fine. Okay. Thank you. All right. So these are the transistor which you see here. So this is basically transistor based temperature sensor, right? And you see the finger is to basically touch the finger on the transistor, and you can actually see the response. So here is the response. So this is, you see, this is like 70 repeated finger touch, and it can actually see that there is a temperature change when you actually touch the temperature. And the response time is also what we measure is something like 24 milliseconds, and the resolution precision is something like 4.3 millikelvin. And the most important part in this development is that the operating voltage. Some noise coming.
Anu, can you please block that?
Okay.
Anu, can you please block that?
Sir, your mic is mute.
Please unmute, sir. Sir, please unmute your mic. No, sir. Please unmute.
Is it fine now?
Now fine, sir. Yes, sir. Yes, sir. Sorry, sir.
Sorry. Yeah. So this you know. Operating voltage is less than 1 volt. The reason I'm putting emphasis on this because all this wearable device that we use actually run by lithium-ion battery, which can give up to 3.7 volt. So if your transistor or sensors are not less than 1 or 2 volt, you cannot actually make it operational like a wearable device. So our operating device is like 1.2 volt. The threshold voltage is less than 1 volt. So this is another important criteria for this kind of transistor. So what you see here is a very interesting experiment that we did with this temperature sensor. So in fact, the very small change in temperature in ambient condition is very difficult in the lab setup. So what we did is that we actually use a mice, and we know that for any mammals, like when you give anesthesia, the body temperature falls by few degree. And what you see here, this is a small animal. So if you give this mild dose of anesthesia, the body temperature falls, which is normally doesn't observe for human being because the body volume is so high that small change may not be able to noticeable. But in case of a mice, definitely we can do it. So what we did is we mount this temperature sensor in the chest of the animal, and then we put a lot of insulators such that it is disconnected from the ambient body temperature on a ambient temperature change, and then we give mild dose of anesthesia. So you see the first dose of anesthesia, so this is his body temperature, and then it falls by a few degree, and then if you just leave it, so it slowly it's recover back to its original body temperature, and then again give second dose, and then again temperature falls down and it's recover. So the important things to learn on this, that this temperature sensor can actually monitor the change in the body temperature very precisely for continuous monitoring. So that is what we actually confirm, that it can actually measure the body temperature variation. And in fact, we measure that like 4.3 millikelvin precision also on this temperature sensor can measure. And then of course, then we thought that why not, like this is such a wonderful device which has extremely sensitive to temperature, very fast in measuring temperature in the body. Why not to develop a technology? So we made the electronics, and we in fact put it in the mask, and it actually measuring the breathing profile, because breathe in and breathe out, these two temperature of the air are different. This such a small temperature difference in inhale and exhale air can be monitored to monitor your breathing profile. So that's what is the started point for utilizing this temperature sensor for medical device. And then we actually detect that how stable they are. So you see that there are 3 beaker of water, so you can dip into the water, and you get absolutely same temperature every time you dip. They're highly stable right underwater, and not only the underwater, but also we measure in different pH solution, we measure in different salt condition, and everywhere we confirm that this device's performance is really stable. So what we can do a lot of things on this temperature sensor. One of the things is like continuous monitoring of body temperature for infants, which is normally done in NICU, like neonatal intensive care unit. So if we have this temperature sensors, we can actually do that. Health quality, BBT, basal body temperature change, real-time monitoring, so everything can be monitored very easily. Now here what you see is that the response of the temperature sensor mounted on a mask, so it can actually monitor your breathing profile. So you see that when you are just calmly sitting, so it's sort of like 12 per minute, which is standard for us. When you're running, you're breathing fast, so it's like 30 per minute. When you are talking, then there is some abrupt change. So it's very precisely can profile your breathing pattern. So what we did is that we developed a device that to monitor the temperature of this inhale and exhale air, because there is some difference in temperature, even humidity also. So and then we actually, just by changing how well you are breathing, we can actually talk about, what is the situation in your pulmonary tract. So the most of the time, what happens, like the people who develop COPD, so their respiratory tract become inflated, and your, the passage become narrow down, and you actually cannot breathe properly. So there is obstruction in the breathing pattern profile. So we can very clearly see, just look at it, and the doctor does that, and that is why the spirometer actually is used, and they can see whether you have what level of obstruction that you have in this case. So this is essentially done because of a lot of effect, including the pollution as well. So the other related problem that can be tracked of this sensor is like, when you sleep, again, most of the time, which is called the sleep apnea, and most of the time what you see is that when you sleep, so this muscle get slot, and because of that it actually blocked this passage, and then we started snoring. And this is very common for many of us, mostly the older age people. And what exactly happened, like when you sleep and your this pulmonary tract get depleted and blocked, you basically for whole in the night you get less oxygen, your body get less oxygen, and this can lead to very serious problem later, which is called the sleep apnea. And you see that it can affect can have any age group. There are other very critical problem for this also are there. You feel irritated sleeping in the whole day, and the most significant problem that we have in our country is, if you look at the data, that 80 to 90% adult with sleep apnea remain undiagnosed, because what you need is to check your sleep. So there is a sleep test lab, and these sleep test labs are very expensive, because we inquired for different labs, which per night cost is like 20,000 to 30,000 to check your sleep. So you have to go to the lab and then sleep there and they test. So this is very expensive, and that's the reason that 80 to 90% problems are not diagnosed. And that we make fun of the people who actually snore at night, but you don't understand, don't in fact understand that the severity of this disease. You see the 82% Indians are not diagnosed because of lack of diagnostic facility available for sleep apnea. This is a 2015 data. So we had something like 34 million people, million Indian who actually have this sleep apnea. Those who are detected, that is the number. So this is very enormous numbers that we have. Worldwide is 1 billion people. So we decided that why not to have a portable, affordable device for this, which can actually replace some of this gold standard, and can be given to every household people at very affordable cost, such that they can keep track of their pulmonary function. The COPD is also another pandemic kind of thing. It's no less than pandemic. As per our data in 2017, it killed 1 million people. It's no less than the COVID pandemic that we had. Over in 2016, there are 55 million people have COPD data, and 250 million people worldwide. So this is also very serious. If you look at this data, some of the data that I got, you see more than 90% COPD deaths occurs in the low to middle income countries, right? Because they cannot test, and the process is also very expensive. And as per 2005 data, which was given by our Ministry of Health, it is there that the cumulative expenditure was 32,000 crore, and this 32,000 crore is like money transaction happens between the patient and the hospitals for the COPD patient. So this is a huge, like one of the annual budget for a whole ministry. Right? It's 32,000 crore. So you understand the severity of this disease. If you look at the other parameter, so in India, so there is 30% chest physician, 70% general physician, 90% general practitioners, and 80% pediatrician. They do not use the gold standard of COPD, which is called spirometer, to test them. So they just based on their some symptoms, they give medicine, and this patient not able to recover, and finally they become COPD patient and cannot recover. So this is become COPD burden. So this is a severe problem that one has to look at, and the assignment that we had taken is to develop something for these huge people who are suffering that. In fact, this had taken a new dimension after COVID, because COVID actually affected lung, which we all know, and the numbers that I showed, in fact, maybe the order of magnitude higher now after the COVID infection, which don't even realize, but our lung had already affected for that. So what you see that we developed this, and so we have now Android app, and you see that, so this profile that you see is constantly monitoring your breathing profile, and so the data is actually uploaded to a Amazon web server, so for cloud analysis, cloud computation, where we actually do AI and machine learning algorithm, and it can very well acts like a IoT based device. So this is few of the prototype module that we are currently, this device is currently under validation. The 3 hospitals this machine is being continuously validated. One is in AIMS Nagpur, other is in Chennai, Subhita hospitals. There also we had taken some data. There is another hospital here. We have a tie-up with NGO also, such that we can do the field trial. So all those things are going on, and we are hoping that in next 1 year you will see this device in the market with very affordable price. Now, what is the for market for this? So I'll just quickly go through, just to give you the background of the work that being a scientist, can also do what are the other kind of work to push your fundamental research into a technology. You see the market survey, and so this is kind of such a big gold standard spirometer, right? You have to go to clinic, and you see the market, right? So there is 6.4% CAGR annual increase in the requirement, right? And there are many companies who make this spirometer, right? And most of the time, you see in any hospital, you go to NDT system, and let me just keep this data. So you see the price, the NDT price is the machine price is something like 1.14 lakh, sometimes 1.65 lakh. So this is the price of the machine, but not only the price, but also important is that to analyzing this data, that is also very important. You need a trained technician, otherwise this machine cannot be operated. And that's the reason that most of the hospital do not have spirometer in their testing unit, because it is not only the expensive, but also it's required a trained manpower who can handle this. Now, if we can have a small device, then of course, patient can do it at home. Even a portable handheld machine can be given to the ASA Kormi and other caregiver in the rural area. They can visit in every home to home, and then collect data, and all the data will be collected to a cloud server, or even doctor can anywhere in the world can actually see the patient's different parameters. So that is what exactly we do. We actually developed a portal for these spirometers. We have user portal, we have employee portal, we have consumer portal, we have doctor patient portal. So this everythings are all done. We have admin portal. So these are all done. So you can actually visit to senflex.in. So this is the startup company that we incubated to commercialize this product. Even we have a consultant doctor portal. So everybody can log into their server, and they can see the data starting from admin to patient. So everybody has their portal ready. So we actually did everything of our own. So these are some of the things that can be done. You have this breathing profile, inhale, this is forced respiratory breathing profile, inhale and exhale, and then finally you get this kind of loop. And from this loop, looking at the shape of the loop, they can say, so this is the normal loop, this is mild obstruction, this is the loop with severe obstruction, and this is loop with restriction. So just by looking at the shape of this your breathing profile, one can tell you what is the severity of the obstruction that you have. And this analysis is not very easy because you will see all these looks are almost similar. But if you use the machine learning algorithm, then the shape analysis is very, very easy and to in the cloud server that the AWS server that we are using. So this is some of the data that I have. So I'll just quickly go through. There is another important observation. Yes. So please also remind me like when I have to stop, okay? Because I have to stop in 6 o'clock, right? So I still have half an hour time. Okay, so you see, there is another important point which is called the capnography. Even this device can give you capnography data, and so capnography data is again your breathing. So basically, this is the profile of your tidal CO2, and tidal CO2 is like when you exhale, what is the concentration of carbon dioxide. This is a different way of detecting, but what is giving is see that these are the data that we have generated from this machine, right? And you see this data has been taken from different patients. So this is a normal patient. So this is a non-smoker, no chronic infection, there's no respiratory problem. So this is exactly similar to the standard profile that you have. But if you look at these two, so these two patients had actually the COVID infection, and you see the profile like shape, they are completely different. And even just looking at this profile shape, doctor actually predicted what kind of complexity they have developed in their respiratory system. So that's another advantage which we can very easily diagnose through machine learning and AI implementation in the cloud. So this is the team. We had the incubated a startup called the Senplex, and we have like 6 people. We have a hardware engineer, we have a doctor also. Me is also there. There is another scientist. There is a software. So we all tie up and develop this medical device. So there is a lot of reports on this, media coverage on this technology. We have live demonstration in Digital India program. We have live demonstration in other Semicon also. So as you see that the funding agency also people came. So this system is taking shape, and we are conducting validation and certifications. Once this is done, and hopefully this will be coming out as a product in the country. So I still have half an hour time, right? Can you confirm?
Yes, sir, you can go ahead. Yes, sir.
Okay, fine. So that's I give you on one example. In fact, there are several such product that we are working on. I just give one example that how you can push the fundamental science that you doing in the lab to develop a technology, validate it, make a product which can be sellable in the market. So it's different ballgame, but if you take if you think that you can do it, then definitely one can do it. So that's one has to take the initiative and do that. Now in the second part, I'll be talking about some other sensors, that how they actually work with organic material and flexible device. So I'll just quickly go through. So this one is like start with the COVID sensor. This is SARS-CoV-2. As I already mentioned that we developed the flexible COVID sensor during the lockdown 2. Second, this is the first lockdown. In fact, the first lockdown we developed this sensor. Let me just tell you how this sensor works. So this thing we already have submitted for patenting, and we published the work also. The way it does is that you take a saliva from here, and this is the sensor, and then we normally put like 10 microliter of water, first a water droplet, and then 10 microliter of your saliva and drop it here. And then we have, this is the organic fed. We have a receptor called ACE2. I'll tell you what this ACE2 is. It actually binds with the virus, and then the moment it binds, it actually the device current changes. And from the device current profile, so this is basically the device current profile. You see, when you put the water droplet, so it shoots up, and then it slows down, and then gets saturated. And when you put the saliva sample, then there is another spike. And from there, how the current is decaying, you can actually tell. So you see the decay time. From the decay time, we can actually tell whether this saliva has a virus or not. That's a simple way. In fact, we have the Android app also, because this is a app-based technology that we developed. Because anybody can do of its own. You like do, even there is no need to go to clinic also. So if you have these sensors, they can do that. How does this sensor work? So let me tell you something that normally, like you have heard that these are the three organs which are severely affected by COVID infection: liver, kidney, and lung, including, like, So what exactly? Why these three organ actually get infected? Because it has some molecule is called ACE2E. So this is called angiotensin converting enzyme 2. So in our body, all these organ walls has a lot of ACE2 molecule, and the function of this ACE, so like you have an ACE and then the ACE2 molecule. So these are two different type of molecule. What they do is essentially, they control the blood pressure. So all these three organ actually simultaneously they work together, which is called the RASS. So RASS is essentially these three organ, they jointly control the blood pressure. So for example, let's say, when your blood pressure is rises, then this NG1 is converted to NG2, and then to lower blood pressure, to increase the blood pressure, this NG2 converted to NG1 to 7. So this is the process continuously going on in our body, such that our blood pressure is constant. And this process is actually done through these two molecules, ACE and ACE2. So what happens? This ACE2 is there everywhere in this molecule. Now, how we get affected by this COVID virus? This spike protein actually binds with this molecule, and the moment this binds, then this virus actually penetrate into the cell. So this is how we will get infected. And what exactly happens is that this S protein is the spike protein here, and they binds with ACE2. So this is the work done 2020 during the work done during the COVID time, and so they actually simulated that. So this is the ACE2 molecule, and this S protein binds, and the moment this binds with ACE2, then the ACE2 helps it to penetrate into the cell, and then they started growing there. So this is how we get infected. So what we did is that we utilize this ACE2 as a sensing material for this, and then we actually let me just keep this some of the thing. Yes. So what we did is that this is the transistor, right? And we used this ACE2 molecule as a receptor of the virus. So we integrated this molecule into the transistor, and then when you actually drop this, when you put this virus in, then this virus binds with ACE2, and moment they bind the ACE2, the current flow through from source to drain will be affected. And if there is no virus, then there is no binding, and their current will be changing in different way. And if there is a virus, they bind with the ACE2 molecule, then you have a different current flow. So this change from the change of the current, then we can actually tell whether your saliva has a virus or not. So what we did is that in this transistor, we use the semiconductor layer, which are pentasim, and you see this is the pentasim semiconductor layer. It's like clear dendrite structure. And what we did is that we exploited the grain boundary of this pentasim dendrite structure, and then through this grain boundary, we put this ACE2 molecule. So when you put ACE2 molecule here, you see this white patches here. So they actually all penetrated into the grain boundary. And when they go to the grain boundary, then you see that this is the grain boundary. This molecule actually coming very close to the conduction channel, which is semiconductor and dielectric interface. So this molecule get access to the conducting channel very easily. And now when actually it binds with the virus, then the electronics environment around that interface actually changing, which is changing the current. So that's a very simple way of measuring the virus. So this is the organic field transistor. Is again, you see this is like, operating voltage is less than 2 volt, such that we can use as a wearable device, portable device, and then you look at the data. So you see, so this is our transistor. So this is the first spike that we get when you actually drop water into it, and then you see if you leave it, then the water, the current actually decreases. So this is your source to drain current. And when it gets saturated, then we put the saliva sample in it. And the moment you put saliva sample, then current again shoots up, but then it decay here. So we actually calculate the decay time, how fast this current is decaying. So now you see from this decay time, there are two decay time. One is the sample having positive sample, and another is the negative sample. So if you have positive sample, then you see that the blue line, which is decaying much faster than the other one, which is actually negative sample. So, and then we calculated the decay time, the TD, and then we figure out that this decay time, and this you see, we had taken 38 patient data, COVID patient data. Their saliva are taken, and then we measure the decay time. So what you see here is that all these red dots, the red dots are having decay time less than 20 seconds. And the blue dots are essentially the COVID negative sample. So they are mostly having decay time above 20 seconds. So that's the detection principle. So if your saliva has a virus, then the current will be decaying, and we figure out from the statistical analysis that within 20 seconds, if the time constant decay time constant come within 20 seconds, then these sample are having virus. If they are coming above 20 seconds, then of course they are negative. But what we calculated also is sensitivity. The sensitivity we found it's 94%, and 94% is because you see there are some blue dot here which actually showed the COVID positive, but they are actually negative. But within the process, we actually didn't see any positive sample as a negative sample. So that's very important. Positive sample showed positive sample. Negative sample, some of them negative sample showed positive, and that is coming within 94% sensitivity. Now, if you look at the antigen-based kit which is available in the market, their sensitivity is something like 60 to 80%. And the sensitivity of the sensor that we developed is something like 94%, which is far better than there. Now, this of course, COVID has gone, so it has no value at the moment. So we stopped this one. But there are a lot of things to learn that we can actually do. We can actually do this kind of protein sensing with this sensor, and then we further develop two other sensors. One of them actually is albumin detection from directly blood, and the second one is also some of the other protein from the blood. So we are actually working on to develop the sensor for one is like cancer, and other is for hepatitis A and hepatitis B and hepatitis A. So these are also trying to develop some sensor with the same principle. So though this was not commercialized, but the technique that we developed for the detection, which are translated to some more relevant sensor development, hopefully this will be also, we'll get some kind of success in this. So this is a point of care detection with similar HSA protein, so human albumin detection. So again the same principle, but in this case, instead of ACE2 molecule, we got a peptide. So peptide actually bind with albumin, and this was our sensing process. So we put the peptide here through the grain boundary, and then we developed that the sensor which actually measure very well. So I'll just keep, since there's not much time available, I'll show you finally the data here. You see. So this is the detection calibration data for different concentration of albumin, right, in the blood. And what you found here is you look at these numbers that pathologically, like directly, if you take the blood to the pathology lab, the same blood we tested in our device also. So the pathology result was like 4.1 gram per deciliter, and our sensor gave actually 4.4 gram per deciliter. So it's very close to the value that you get in the pathological laboratory. And what you find here is, what is the advantage? You see that it doesn't need to extract out the same amount of the blood. It directly drop 10 microliter blood from your finger to the sensor, and it takes, you see, something like 100 seconds, like 1.5 minutes, you'll be able to say whether what is the concentration of albumin level in your blood. So that's absolutely a device which acts like a point of care device, and it's minimal invasive, right? It doesn't need to go to the pathology for that, and there is a mass screening where mass screening is necessary. This kind of technology will be very useful because it can immediately keep without further any chemical process of the blood and the albumin level to it. So I think I'm going to stop because there are a lot more things to show, which I'll not discuss anymore. Maybe I can take a few questions rather instead of covering more topic. Thank you for your attention.
Thank you, sir. Yeah, so now it's open for discussion. Any questions from the audience? Yeah, Rajalakshmi Kannan, you have raised your hand. You have any questions? Rahul Kumar? Anu?
Yeah, please unmute and then you can ask.
Yeah, you can unmute and you can ask the questions, if any. Right. So I think it looks. So if you can post the question chat box also.
Yes, you can do that.
Anu, any questions in the chat box? No. Okay. So.
I would like to thank Professor Deepak Kumar Goswami. Professor,
Yes,
thank you
please.
so much.
Yeah, thank you so much. Yes.
We have now come to the end of our 6-day faculty development program. I request all, we have a small valedictory session as well as.
Thank you, sir. Thank you so much, sir. I'll contact you. Thank you so much. Okay,
Thank
sir.
you,
Please, sir. Thank you.
So I can leave, right? Yeah.
Yeah, please, sir.
Okay, fine. Thank you.
Yeah. Anu? Yeah.
We have now come to the end of our 6-day faculty development initiative, Organic Semiconductor Innovations. So I request all, we have a small feedback and valedictory session. I request all participants to switch on their cameras and please share your feedback with us.
Please, we need a few feedbacks.
I request all participants to kindly switch on their cameras.
So once they are switched on, you can take a screenshot. So actually, we need actually feedback from the participants. So who are all interested to give feedback? Dr. Rahul Kumar, are you willing to give? You can unmute and you can talk.
Good evening, Professor, and thank you for the organizers to organize such a wonderful sessions in the FDP.
So Dr. Venkatesh, please go ahead.
Yes, Professor. Thank you, Professor. And all the sessions are very informative and thought-provoking. And I am a organic chemistry background, Professor, but I learned a lot of things in other domains also, because now research is a multidisciplinary research nowadays. So thankful, I am very much thankful to the uh, Central University Thiruvarur to organize such a wonderful, informative FDP session. And I thanks AICTE ATAL organizers. Thank you, madam. Thank you, sir. Thank you, Professor.
Hello, Nagarajan sir. Hello.
Yes, please, sir. Yes, please, sir.
Sir, I am Dr. Selvakumara S.
Please, sir.
Anurag Engineering College, Kodada, from Telangana State, sir. First of all, I would congratulate all the organizing committee, those who are successfully conducting for this excellent program, sir. Really from this session, especially these are the semiconductor field. I am learned a lot of things and new innovative things. Really very thankful to the organizers, especially Jan Prakash sir for their patience. Really good session, sir. I hope in future also we expect the same thing from your university, sir. We're expecting a refresher course also from your university. Thank you, sir. Jan Prakash sir, congrats for excellent organization and for grand success of this program. Thank you, sir.
Yep, thank you, sir.
Sir, one more kind request, Professor, Dean and Professor, Dr. Nagarajan sir. In future, if you can organize a workshop, please organize a workshop, then it will be good for us, sir, so that we can get a hands-on training in organic semiconductors. Please, sir.
Okay, sir. Okay. Sure, sir. Actually, we are planning to conduct a 2 days international workshop on 3rd and 4th of February 2025, sir. So we got funding also. So it's actually a kind of a lecture workshop. So we have a speaker from Japan and all. So 2 days we are planning to have. There's no registration fee. You are most welcome to come, right?
Nagarajan sir, one request from our
Thank you, Professor. Thank you, Professor.
Sir, please conduct one workshop or FTP or refresher course, whatever may be, depending upon your possibility, on the topics for undergraduation level, sir, because the maximum of the participants are from various colleges who are teaching for the UG students, sir.
Sure, sir. Sure, sir. That also we are doing side by side, but that is on core chemistry.
Yes, sir. Because it is
that
very
we are doing on core chemistry
also.
subjects. We are doing. Now we have a WhatsApp group. Whatever the workshop we are organizing, we will be sharing to you, sir.
Sir, look at that workshop by including practical sessions also. It is better, sir.
Sure, sir.
We're all from different engineering or UG colleges, sir. These are helpful or to improve our teaching standards also.
Sure, sir.
It is our request, because through this we can carry our sessions to the student level also. Not only for us, it is helpful for the students also.
Sure, sir. Sure, sir.
Thank you, sir.
So anybody else want to say anything? Yeah. Who's there?
sir.
Yes, sir, please.
Good evening, sir.
Rajkumar.
Yes,
Well, I would
sir.
like to take this
Evening.
opportunity
Yes,
to take
I
my
would like to
sincere
take.
gratitude to the organizers of
Yeah.
this faculty development program, sir. From the past 5 days, we have been incredibly enriching, and I feel privileged to have been a part of this program, sir. And I would like to thank the organizers for their tireless efforts, sir, and in making this program successful. Thank you, sir. Thank you once again, sir.
Well, welcome, sir. Please. Now, Rajkumar, Dr. Rajkumar.
Yes, sir. I hope I enjoyed all the 6 days FTP in a very nice manner. So I would like to thank both Professor Narajan sir and John Prakash sir for organizing this event day and night. So I hope I'll enjoy many things, not only chemistry in all aspects like technology and physics and so many things, softwares and other applications. So I hope you will conduct many more programs in this upcoming.
Sure, sir. Sure, sir. Sure, sir. Anybody else want to say anything? Okay. So can you please switch on your camera for a while? We want to take one screenshot. Anu, you can take a screenshot.
Yes, sir. We are recording it, so it will be.
Yeah, it will be done, right? Okay, okay. Yeah. So anybody else want to say any feedback? Madam?
Sir, thank you for all the organizing committee for conducting
Ma'am, you
this.
introduce yourself, ma'am. Where you are from?
I am from CRR Engineering College, Eluru, sir, and also a research scholar from Geetham University.
Oh, nice. Nice, ma'am. Yeah.
Thank you so much, sir, for organizing this very knowledgeable FDP and handling our queries so patiently. Honestly, through this FTP program, I had learned a lot to make myself sound in the field of semiconductors, sir, which is a need of this hour in anyone linked to this education field, sir. In future also, I want to join all the FDPs that are conducted by your university. I am very glad to be a part of it, sir. Thank you so much, sir.
Thank you, ma'am.
Thank you, sir.
So anyone else? Okay. Anu?
I have a few announcements.
Please.
We had 3 sessions today, so we have 3 feedback forms as well as an overall feedback form. So there are 4 forms. I request all of you. All forms are active right now. It has been shared via Google Meet as well as in YouTube Live. So I request everybody to fill the forms. And regarding tomorrow, the exam, you'll be receiving a mail at sharp 6 p.m. It will be you can answer the questions between 6 p.m. today to 6 p.m. tomorrow. You can log in to it any time. It will be timed for exactly 45 minutes. There will be 30 questions, 30 questions of, and each question will be for 90. You'll receive 90 seconds for answering each questions. And there will be, you cannot go back to one question after answering one. So there are a set of rules it will appear. So kindly look into that. So you have received, I hope you have received the mail. If you have any doubts regarding that, you can ask in the WhatsApp group. We have come to the end of our 6-day Organic Semiconductor Innovations Faculty Development Initiative. I request Professor S. Nagarajan to kindly deliver the valedictory address.
Yeah. Thank you, Anu.
But we have received only 3 feedback forms in this today's session, sir.
No, actually, the last 2 feedback forms have been sent together and they're active right now. We'll send it again if it in this Google Meet chat.
Okay, ma'am.
If you have a doubt.
Yeah, thank you, Anupama. So actually, indeed, it's a pleasure, right? So last 1 week, evening 6 o'clock, I know there are difficulty in attending the FDP at odd hour, evening 6 o'clock to 9 o'clock. I think many of you might be traveling or doing something. And as far as female faculty, they may be working in kitchen also, right? Anyway, you listen to us and listen to many of the resource persons, our resource persons talk also. So very good evening to all of you. So thing is that we started the FDP with Professor Satish Patel. So he gave a brief idea about organic electronics. Today we end up with Dr. Deepak Kumar. So he's an application scientist. So initially we started Satish as a basic science to the applied science. So hope you may be knowing or not, the IIT Kharagpur is one of the renowned laboratory for organic electronics, especially the flexible foldable electronics. You can visit their website. They are doing plenty of research in this domain, right? So actually, when the ATAL AICTE notified for this kind of a workshop, so we were interested to apply. Then initially we thought of going for a different title. But later we decided, okay, the semiconductor is a booming research area, right? At least we can start with organic semiconductors. That's why we made this FDP. We made a proposal also accordingly. And for your information, some institutions in India, now they have started offering elective courses on organic electronics. In many IITs they have, and many NITs they have, and many engineering institutions. Even some physics department, they are offering courses on organic electronics. Right. So this is a kind of now it's a kind of an elective paper in many institutions. I think many of you may be from engineering colleges. You can also think about that. Or otherwise, a part of it can be included in the curriculum, because the purpose of attending FDP is you can pursue research. If it is not so, at least you can add little to your curriculum wherever if it is possible, right? So this I don't want to drag it for more time, because already it's 6 o'clock. You are attending from 2 o'clock onwards. So with these few words, I thank all the participants, because success of the program depends upon the participation of the participants. Really, everyone participated. Thank you one and all. I thank my colleague, Dr. John Prakash, because he's the person behind everything. I thank you so much, Dr. John. I thank Dr. Anu. I thank Akshaya and all my research scholars for putting their effort. And I thank my institution for supporting us. I thank AICTE for providing funding for organizing this 1 week program. And I thank you one and all. Thank you so much. If at all anything, you can WhatsApp me or you can message me. I think the certification, everything will be done by AICTE. I've been told like that. If at all any difficulties, you can approach me at any point of time. Thank you so much. Thank you one and all.
Thank you, sir. Thank you to all the participants.
Okay. Bye now. Thank you.
To the participants, we have shared all the videos for all the lectures in YouTube as well. So if you go to the live link, you can watch them at any time. So they are present in YouTube. Thank you.